Maybe you have an outdoor wedding in Nashville in December. So wouldn't it be nice if you could just use a text prompt and generate a garment that fits that occasion and that actually fits you as well, as actually I was motivating earlier. Maybe you have an image that goes along with that. Could be a sketch, could be a photograph of your favorite movie star, and you want to get that same dress or that same suit tailored to you. A foundation model for garments would be a generative neural network that basically takes potentially multimodal input, such as text, images, or other types of input, and then outputs not only an image of you wearing this garment, but an actual sewing pattern that would be able to you would be able to fabricate so that you can actually wear it. So the garment industry has been around for hundreds of years, and companies like LVMH, for example, are some of the most valuable companies in the world. But AI is not really something that has made the way into that industry. So we are to do something about that. One thing to think about is like, what is the right representation for these garments? And the natural thing that comes to mind are sewing patterns. So what is a sewing pattern? Many of you might be familiar with this, but I just want to briefly define it. A garment or a sewing pattern in this case are basically multiple 2D panels. Each panel is flat. It is a closed loop of parametric curves. It's basically like a vector graphic, but it additionally has stitching information. So specific edges are stitched to other edges, so you can actually sew them together. So that's different from vector graphics. And the sewing pattern is sort of like the natural language of the garment industry because it's used for the design, pattern making, the actual fabrication. So it is a natural representation that comes to mind. And in collaboration with Maria and a couple other folks, we wanted to basically try to implement the first version of this vision of a foundation model, a multimodal foundation model for digital garments. And the basic idea is that the model, again, will take text or images or both as input, process that, and then generate a sewing pattern. The sewing pattern itself is very useful, but there's a couple of other components of this pipeline that you sort of need, which include the draping simulation. So how do you take the sewing pattern, stitch it together, and drape it on a digital mannequin? How do you then simulate that also so that the digital mannequin can move around? And then you can enable a variety of applications such as text to image generation, text to garment generation, image to garment generation, text and image, but also garment editing. So can we take an existing garment and adjust the size, adjust the layout, or the style of this garment? And so this is what we set out to do with AI Corel, which is actually a paper here, a highlight that's being presented in the next couple of days. So I encourage you to go to the poster. It's more like a sort of a high-level overview. Apologize for the compression artifacts in my PowerPoint. That happens to looping videos in PowerPoint on Mac. If anybody knows how to fix that, please let me know. But the basic idea is that you can then simulate these digital people and enable capabilities that are well known from the natural language processing community, from image generation community, and so on. That's specific to garments. So why is this a good topic to work on now? I would say last year was really a key moment in this community because Maria basically created Garment Code Data, which is a procedural garment generator that allows you to generate a ton of different sewing patterns procedurally, right? And then you can drape those onto mannequins, render them, and the data set is really enabling because it's a first large-scale data set that contains about 130,000 patterns and renderings, corresponding renderings of draped parametric humans. So it's not quite photorealistic, but it is a first starting point where we have many different types of garments, including tops, shirts, dresses, jumpsuits, skirts, pants, and so on and so forth. So this data set is the beginning of the AI era of foundation models for garments. And that only happened last year. So we teamed up with Maria actually to extend this data to a data set called Garment Code Data Multimodal. It's basically Garment Code Data with additional text annotations for the renderings. So ideally, you want to have sets of sewing patterns, corresponding renderings, one or multiple renderings of a digital human wearing these garments, but also text description, because that allows you to train a text to garment generation model on top of that. So we made this available as an add-on basically to Garment Code Data, and then it's 120,000 text, image, and editing pairs. We have a small set of editing data also where you have the same garment edited to different sizes. So this is useful for supervised fine-tuning on editing tasks. One big question then is like, how do you actually represent the sewing pattern so that you can extend a multimodal foundation model to be able to model this as an output? And there are multiple different ways of doing that. The way we did it in AI Parallel was we take the sewing pattern and we treat it as a special type of a vector graphic. And we basically think about it as a vector graphic. We are inspired by the literature that has come up in the domain of vector graphic generation. And we extend these methods to include garment-specific information. So what we basically need is a tokenizer that takes a garment as an input, the sewing pattern, and creates, encodes or decodes it into tokens, and like any other output modality, and fine-tune our foundation models with that. So the garment tokenizer that we came up with is basically an autoregressive token generator that has a couple of primitives that include 4 types of edges. So there are lines, quadratic splines, cubic splines, and arcs. This basically models segments of the closed loop that represent each panel. We have special tokens that define the start and end of the panel in a token sequence, as well as the start and the end of the garment itself. And then the important thing is the stitching information. So you can find a little bit more information on the technical details of the tokenizer in our paper, AI Parallel. But the basic idea is that we need to model the stitching information so we know which edge of one panel belongs to which edge of another panel. And this tokenizer allows us to basically learn sewing patterns, so the garment language. And we can now encode garments into tokens and sort of treat it in the same way as we treat tokenized images and text. And we can then train a foundation model of fine-tune it on this. At the time when we worked on this, which was about last summer, the best open source model that we're able to work with was Llama. It's basically a multimodal version, open source version of Llama 2. And the question then is, how do you fine-tune it? I will refer to our paper for details on the specific way of fine-tuning it. We have made the model available on our website, so you can actually use it and download it. We have the original Llama version, and we also have a new and updated version that is based on Llama 3. So it's a much more capable model that will also be, that is already available on the website or will be very shortly. I'll just show you a couple of results. It works even for some types of images that are sort of captured in the wild. So if you have the input here of a person wearing a dress and you're saying, hey, give me the sewing pattern for that, there's a couple of baselines that we need to beat because it's not a new setting, image to garment generation. Dress code was a paper from SIGGRAPH last year, and dress code is doing an okay job. It gives me something that at least looks like a dress. It doesn't look very similar to the original dress, but it's doing something. SewFormer is also an image to garment generation method. In this case, the skirt part failed to drape, so you don't see that on the actual garment. Our model works fairly well. It's the closest to all the baselines, is nowhere perfect yet. So I think about this as a first step towards a foundation model for digital garments. So this is the image to garment generation setting. We also have the text to garment generation setting where our input text can be either a short description or a pretty detailed description of a garment. And it's a little bit difficult to evaluate this kind of a setting, but the sewing patterns that are generated by our model based on these text prompts look very similar to sewing patterns that we use where we have the reference. So again, this gives us the ability to generate digital garments using text and image or image to garment generation, but we can also do things like the editing task, which is particularly interesting also. All right, more recently, we've been training the Llama version of this, the Llama 3 version, which is much more capable model. So before we had Llama with multimodal input and generating the sewing pattern output. The Llama model it came out after we actually submitted this paper. We extended our tokenizer and our data set and the training routines to this type of a setting. This is actually a workshop paper that was presented this morning, but you can look it up on on arXiv. It's been up for a little while. And the basic idea of all these foundation models, of course, is to transfer the knowledge that the model has learned from web scale text and images that it's seen during the pre-training stage online, and transfer that knowledge to the new task of garment generation. So think about it this way. You say, hey, I want a garment that makes me look like Caesar for next Halloween, right? The model has to reason about, oh, who's Caesar? Caesar was a Roman emperor. What time did he live in? What type of garments would these people kind of like wear? It needs to like reason about the thing that I'm asking you to do and then generate the garment. So we did a lot of evaluations on reasoning capabilities of different methods, including Soformer, dress code, and AI4L, and found that the reasoning capabilities of this Llama version of our model are very high. And that is a good sign towards reasoning, garment level reasoning and garment understanding. Okay, that's as much as I'd like to say about garments. We've worked on a lot of different types of methods of modeling digital humans too, because when you think about virtual try-on or related tasks, you need to think about the garments, but you also need to think about the humans wearing those garments. So very simple mannequins are good, but it would be better to have photorealistic capabilities. So we started working on this topic maybe around 2019, and at the time, the training data for at least training 3D objects for digital humans was very limited. We basically had Observerse, which was amazing. It's a great data set, 10 million different assets. However, they're all computer generated. The measures aren't very good. There aren't any high quality humans in there. So we can learn how to generate, computer graphics like simplistic objects, but this isn't enough. At the same time, we've gotten a lot of real data online. For example, FFHQ, the data set from NVIDIA, has 70,000 photos of humans. It's very diverse, not huge, but pretty big. But we only have a single image per person. So the big question back then was, can we learn a 3D generative model from single view 2D observations? I'll show you that we can. At the same time, we now have a lot of data sets that are sort of drone type data sets or multi-view image data sets where we look at static 3D scenes from multiple different observations. And that's really good for multi-view consistency and things like that. But it's sort of hard to learn actual humans from this setting because, again, we don't have enough humans. There are companies like Meta who have acquired a large amount of multi-view video data sets of real humans. But the problem with these data sets is that we can't get them. So they don't want to give it to us. So that's challenging. So the best thing we were able to do at the time was to use the real data, single view images of real people online. And this is in the age of GANs, seems like many moons ago. But GANs are actually interesting and capable, and they can do things that diffusion models can't do. I'll talk about diffusion models later also. But at the time, we realized that to train a 3D GAN on 2D data, we need a couple of things. We need a 2D generator. We need ideally a 2D discriminator, just working on the images because we had good architectures for those and enough training data. But we need to create a 3D inductive bias for the network so that it learns to generate something that's multi-view consistent. But it has to be very efficient. So we came up with this representation that we call the triplane representation. It's basically 3 orthogonal planes. Features, 2D features live on these 3D planes, where we can query the volume by projecting each 3D point onto the 2D planes, aggregating these features, and then decoding them using a nonlinear network. So this is like an implicit decoder that's very fast. And this allowed us to basically take the existing style GAN 2 architecture and turn it into a 3D style GAN type generator, trained only on 2D data. And the type of results we got at the time, this was a CVPR 2022 paper called EG3D, were actually pretty good. So it's close to photorealistic, I would say. Not quite. There's an upsampler in there, so you see some aliasing artifacts maybe in the hair and accessories. Interestingly, the model learns to, represent things in 3D, so we can actually decode the 3D information, even though the model has never seen a depth map or any 3D information during training time. So this is totally unsupervised. The diversity of the generated humans is fairly large. This runs in real time at inference time, so you can, generate new digital humans in real time. It not only works on humans, also works on cats, which might be interesting for some applications. The results that I found most astonishing at the time were that this is a latent generative model, so it maps random latents to identities, basically. None of these people actually exist. This is not a reconstruction task, really, it's a generation task. And we can interpolate the latent, the noise vectors that represent each of these identities. And so with that, by interpolating the latents, we actually get really well-behaved latent space that we can interpolate. And that's something that diffusion models, for example, can give us easily, along with this real-time performance. The other thing that we can do with, again, that we can easily do with the diffusion model is that we can mix and match generative parts and model parts. And what I mean by that is we can model the lighting and shading information, for example. We can dial in a physically based lighting model, such as phone lighting, a simple phone lighting model. And instead of generating the raw pixels, we can generate normals, albedo, diffuse, specular components, and then use an explicit lighting model to combine them and get the lit version of the character. And if we do that during training time, at runtime, we can create different identities, but we can explicitly control the lighting scenario also. So we can use environment maps and relight these characters explicitly, in addition to changing the camera. So this is an example of this. We can directly control explicitly the camera, and we can also explicitly control the lighting. And this altogether resulted in capabilities that didn't exist at the time. So we call this LumiGAN. So what about generating full bodies? Basically humans that garments, accessories, and so on and so forth. This is actually pretty challenging because the faces are easier in the sense that they are easily aligned. Most people have, faces that are sort of similar. Everybody has a nose. Most people have 2 eyes, 2 ears, a mouth. Yes, we all look different, but to some extent, the general structure is pretty much the same. And most of the face doesn't move as much, maybe except for the lower jaw. So it's easy to sort of align all these face images. But for bodies, it's very different. You see humans in the wild with vastly different body poses, moving their arms and heads. They wear all different garments. They have accessories like bags, or wear helmets or hats. They were riding bikes and so on and so forth. So it's actually pretty hard to align these, and that makes it challenging for a GAN to work with. GANs are very good at domain-specific generation, but they don't work as well when the diversity of the data is too high. So we came up with a method to, again, sort of hack the graphics pipeline into the generative pipeline by learning to generate 2D texture maps on what we called a Gaussian shell map. So this is a simple template, and it has multiple layers. It has several inflated and deflated versions of the simple template. You can use linear blend skinning to actually animate this character, and all the layers will move with it. And then we populate Gaussians on these different layers, because the Gaussians sort of give us a close to volumetric representation around these discrete surface layers. So what we're generating with our generator on the left are basically texture maps, UV maps for each of these layers. And each of these UV maps contains the attributes of the Gaussians that are then sampled on the layers and can be animated. And this way we have sort of a mix of a 2D CNN-based generator with a directly, explicitly animatable and renderable layered Gaussian representation. So we're actually doing Gaussian splitting again. That's what's being rendered, but what's being generated are these UV textures. And then we can use standard 2D discriminators to train this model. So this allows you to generate digital humans. Once they're generated, you can again do this interpolation that I showed you earlier for the faces. You can also animate these characters directly using linear blend scanning, which works pretty well for people wearing relatively tight garments. And you can transfer motions and things like that. So it's a pretty interesting approach to generating these types of characters. And for 3D aware generation, this was the state of the art, at least last year. obviously the world has moved on from GANs towards diffusion models. And so now is the era sort of video diffusion models. We've seen tremendous progress on now generating videos of all kinds of things, including digital humans. So then the question is like, can we enable consistency of these characters for the video generation and enable effective control of that too? So again, simple can be useful in this case. And in a new paper that's going to be presented at SIGGRAPH this year called Interspatial Attention, we used the simple template for two things. We used it to condition the video diffusion model that we trained from scratch in an academic setting. So, the quality isn't going to be perfect, but it is trained from scratch. So we did all the pre-training, and we also designed the VAE from scratch. So keep that in mind. We used the simple method, the simple models to condition the video generation model. So that gives us control over the pose and expressions of these people. And then we designed a new attention mechanism that enables consistency because it uses the correspondences between the frames given by the parametric template that we have to condition it basically in 4D. If we have this mapping from 2D pixel locations to the 4D template or the 3D template that's deformed over time. And we built an attention mechanism around that basically helps guide the attention towards this using this correspondence. This is what we call interspatial attention. And it basically bridges the 3D simple template with the 2D videos in the attention mechanism itself. And it does that using the positional embeddings of the transformer architecture. So the positional embeddings are modified in the sense that we extract 2D positional embeddings from the videos. We extract 3D positional embeddings or 4D from the 3D template, from the simple template, but we're projecting them into these into the same space. So it's the positional embeddings of 3D and 2D live in the same general space, and then we inject those into the attention mechanism. And that really helps with the consistency. And also works better for generation than the baseline control net. So here's I apologize. But on the left, we see the conditioning information. These are the rendered template meshes that we use to condition the control net in the middle. Control net works okay, but it doesn't always follow exactly the control pose, basically. Our 3D attention mechanism is a lot more faithful to the conditioning information and gives you better quality for this baseline. It works for generating individual persons. It works for generating multiple people at once, which is something that isn't really easily possible typically, because if you see occlusions or people walking in front of other people, you often get identity shift or drift. We can generate faces. We have camera control. We actually have background compositionality too. Not sure what's going on. It's compression or fast. We can do upper body. So we can control basically anything that is controllable by any kind of, in this case, parametric template. Okay, so I've talked about garments. I've talked about digital humans. So obviously we want to do them both together and do digital garments and humans. So this is something that is an interesting challenge for the future. Last year, we took a first step at this, and this is more of a reconstruction problem instead of a generation problem. And the question that we had was, can we learn better dressed avatars from multi-view video by differentiating not only through like a template model like simple, but through a differentiable garment simulator itself. So this is interesting because you can basically take just a few observations of a person, which in this case are multi-view videos, and what you get out, oops, sorry. So the input of multi-view videos of this person, and the output is the, well, dress avatar, but we have an explicit mesh representing the garment, and we also regress the physical parameters of the garment, of the fabric. So that allows us to basically generalize to much different scenarios and take this character and put them in completely novel scenarios, and while with this physical simulator, and then basically learn to render them in novel positions and generalize well beyond the observations that we have. So these generalization capabilities to motions that were not observed during the training time, which is really just the video of her moving around, are really incredible the more physical structure we or of the garment simulator we introduce here. So we can do things like change the camera position, directly edit the body pose, but also change the lighting. All right, so what are some of the open challenges in this domain? I mean, I think high quality and physically accurate garment reconstruction, or let's say digital human and garment reconstruction from images and videos is an open challenge. Ideally, we want to be able to do that fast. So just from monocular video, you should be able to reconstruct the garment. And I haven't seen too much work that does that well. We need to improve procedural garment generators like garment code data. It's typically currently doesn't model things like multi-layer garments, pockets, frills, collars, buttons, all the things that we care about in real garments. So it's a really enabling tool, but it needs to become more realistic, let's say. And then we need more data, obviously. We need more diverse and realistic data sets of garments and humans, and we need to incorporate metric body sizes so that we can do things like editing, virtual try-on, and all these different things. So this is sort of an idea towards a foundation model for digital humans and garments, and I think this is a really exciting area to work on right now. In my lab at Stanford, work on topics related to neural scene representation, rendering, and generation, but we also work on physical systems like VR, AR wearables, and computational optics and imaging. So thanks to all my collaborators and students who did all the work, and thanks for you for attending.
We do have time for questions. If anybody wants to ask any question, please raise your hand or come to the mic. Okay, we have one.
So wondering how many data set do you think will be sufficient for us to actually build a foundation model for human and clothing?
Okay, let me just talk about the garments first. I mean, with a procedural model generator like garment code data, we can generate an infinite amount of data. So it's like a simulator, right? We can create infinite data, but there's just like in robotics or in other fields, there's going to be a sim to real gap. So we can try to close that gap and improve the simulator to make it more realistic. And that's definitely one big approach for how to get towards, well, creating lots of realistic and diverse data. The other approach would be to think about, what is the type of data that we already have available online? And that includes text, images, and videos. And then the question is, can we label those data in a way so that we can use it in a meaningful way for supervised training or fine-tuning? And so there, I believe that there's a rich source of information like images and particularly videos of humans wearing garments, but we need to label them. So labeling them with simple is something that a lot of people are working on and works sort of okay, but it's actually not a solved topic yet. Even looking at a monocular video and accurately fitting simple into videos in the wild. And then I think the next logical step would be to think about garment reconstruction from monocular videos. If you can do that at scale, that would give you a nice potential data set for these foundation models. And these are just two different directions, going towards, simulated data, make it more realistic, or going from real to sim type data where you start with videos and then you label them with sewing patterns and you reconstruct the sewing patterns. But that's much more challenging technically. But I think those are the obvious directions in the future to get the data that you want.
The question there is if there is a middle ground. Right, and then text is another really interesting question because text labeling is ambiguous. And I'm sure you already have seen in all these imaging fabric material, they are continuous, they are not discrete.
Yes.
And so there is a question, I think sim to real gap is a real one, and partly because simulation are discretized, lives in a discretized space, real world lives in continuous space.
Right.
And so that discretization is really what leads to the sim to real gap. Now, if we rely on text, we're just going to add another layer of discretization. And so I'm not 100% convinced that text is a good interface, but whether that's going to really narrow the sim to real gap.
I mean, text is always interesting because we have a lot of it and there's a lot of interest in large language models. How useful is text to garment generation really? I don't know. I think the editing tasks are actually probably more interesting and thinking about metric body sizes and so on. There's also a lot of applications for foundation models for virtual trial that don't need sewing patterns at all. And then you can just get away with unlabeled video or image data. So I think there's lots of exciting applications and not all of them need the same capabilities. But I like to think about the sewing pattern also as a path towards fabricable garments in the long run. It's not something that we have done so far or that I've seen too many other people doing already. But I mean, eventually I'm excited to bring the digital world and the physical world together. And in this context, that means going beyond virtual try-on towards actually fabricating the garment, going to the foundation model, sending it to my local tailor, and then getting the garment back to my place, right? That's the vision that I have. And so for that, we need this sewing pattern.
Totally agree.
Okay, thanks. All right, I think my time's up.
Yeah, I think let's thank Gordon again for the very interesting talk. Next up, we have Michael Black. Well, Michael doesn't need any introduction, but for the sake of the workshop, let me introduce him. He's an honorary professor at the University of Tübingen and one of the founding directors at Max Planck Institute for Intelligent Systems in Tübingen, where he leads the Perceiving Systems department and serves as the managing director. He was also a distinguished Amazon scholar and a VP from 2017 to 2021. He's a recipient of the PAMI Distinguished Researcher Award and all three major Test of Time awards in computer vision, including the 2022 and 2010 Coendering Prize, the 2013 Helmholtz Prize, and the 2020 Longuet-Higgins Prize. He's a member of the German National Academy of Sciences and a foreign member of the Royal Swedish Academy of Sciences. I think this introduction is going to go pretty long if I keep reading, so let me stop and welcome Michael to the workshop, and we're looking forward to your talk.
Thanks. Yeah, please have it.
Before we get started, the Zoom link didn't work on the website. Okay.
Yeah. Can you please log into the Zoom?
Well, I tried that and I followed the link. And it just takes me back to the conference site.
Okay.
It's the same.
I think you have to log in.
Oh, I don't know how to log in. This is my 6th workshop in 2 days and I had no idea how to log in to. Okay, all the other ones worked. We went to log into anything. We tried this. I don't know if I have to log in. What would it be? CDPR? No, I don't have a login.
Do you prefer to use your own laptop or do you have your slides on cloud that you can?
I only have them.
Okay, let's do it with them.
I do have a version in my pocket, but I would prefer to use.
Sure.
Can. CDPR line, where would that be? Email visit.
Yeah, I'm trying to do that.
Apologize, folks. You'd think after doing 5 of these in 2 days, I would know what I'm doing. By the way, while we're waiting, I just love Gordon's talk. I really do. I really love the interspatial attention stuff. I wish we had been bold enough to do something like that, but the fact that we trained it from scratch is amazing. It was not good. But you did it, and that's really, really inspirational. So totally love it.
I'm trying to pull up the information and send it to you via email.
Do we have people on Zoom?
Yeah, I tried to contact the ACV. Yes, we have people on Zoom and I tried to contact the ACVC staff here, but they're not very
Can they just send you the link that they're,
Yeah,
or will I be able to use it? I mean, I can't click your link on the website.
yeah, that requires registration. So, I mean, it's supposed to be logged in.
So if I
That's
have
what I'm saying.
CPR registration of that. Alright. And for registration. Registration link.
And actually, you couldn't stream it on your laptop with Zoom.
Yeah.
Yeah, I can do that.
Because I tried to log in when I couldn't come back in time. That registration website isn't quite, if Michael tried to do the same, it's probably not gonna. And when I tried to ask them to reset a password, they never sent it to me.
Okay,
So I think it may be easier,
just,
just simply switch, transfer.
sure.
It's, even if it's not a final file, it might be easier just to switch.
Give me a second here, I have my registration document,
The original registration URL, you have that.
the original registration URL. The CBS.com.
It's, you need a whole entire, thing for the Zoom link. That's what he needs. Does anybody, well, the other thing is to send a Zoom link to him.
Yeah, I just sent it to him by email.
Oh, then that might be easier, because I tried to get that.
Sure.
Okay. Not here. This one here.
Yeah, let's try it. That
Open in Zoom. Da-da-da-da-da-da. Okay. Now I know what to
Great.
do.
Great, we're all set up. Sorry for the delay and thank you for your patience. Michael, it's all over to you.
Share. We're back. And speedy because,
We lost 5 minutes.
we lost 5 minutes. All right, so, since it's a workshop, I will present some stuff that's new work and, that maybe you haven't seen before. But I think workshops are good to just also get people thinking and, maybe create a little bit of excitement for the panel discussion that will come later. So, I want to talk about the myth of virtual try-on. So it's pretty clear what virtual try-on is, right? You show people realistic images of themselves in clothing. It mimics the real world experience, virtualizes the shopping experience, and it just seems obvious, right? That's why we're all here, because we think virtual try-on is a good idea. But if you go around and ask people, what's virtual try-on for? Well, actually, I want to ask you, what's virtual try-on for? Why? Does anybody? Why do you think it's a good idea? Why are you here? Anyone?
I want to order a correct size.
You want to order a correct size, so it's about sizing and fit, okay? Is that the same for everybody? Is it about sizing and fit?
Diversity,
The what recipe?
diversity.
Diversity, you want to see that's good, that's a good one too. So you want to see it maybe on somebody who's more like you, presumably.
Yeah,
Or
and
I just want to see
different,
it on other random people, or
I mean, just me, but
that's just me,
Yeah.
more like me, but maybe not
I
exactly.
want to have an advisor who advises me on which gardens.
You want a style assistant, because,
Exactly.
yeah, you need one. Anything else? Larry?
Wrong combination, that you couldn't have image explicitly.
accommodations.
Combination.
So that's a style thing. So we've got style, diversity, fit, and assistance. Okay, so great. Lots of reasons for this. Other things you might do is want to drive engagement, just have somebody spend more time on your site. You might want to increase sales through this. There's a lot of customer apprehension to buying clothing online. Maybe you want to reduce that. It's about style, it's about fit, it's about reducing returns. I didn't hear that one, but that's kind of the combination of style and fit. And there's a lot of times it just kind of this unspecified, it just feels obvious, right? It just you'd like to virtualize it. Let's get rid of the changing room for that. Well, fortunately, Lands' End did this. All right, they were the first company that I know of that had an online virtual try-on solution, and this was in 2007. Okay, and they used something called My Virtual Model. You created a model of yourself, and then you could try on swimsuits, and swimsuits were a great thing to try because you didn't have to do all this complicated clothing simulation stuff. It's just a texture, right? So they just put a texture on the body, and they were doing it. So how did it work? Well, in the words of one of my friends, my virtual model allows you to make an uglier version of yourself so you can see how ugly you will look in their ugly clothes. That's her review of the website. And it turns out nobody bought anything. Because, you know, the truth of the matter is, you go into the thing, you're going to the beach, you gotta have a bathing suit. You go into the change room, you don't look good at any of them. You don't feel really good about yourself, but you don't need your bathing suit, you buy one of them anyway, right? Because you have to. But if you're on the web, you just stop. So look, you might say, well, Lands' End, you know, so Lands' End, let me continue with that because they produce this catalog, right? And the catalog, you know, Lands' End caters to their customer who's an American, US citizen, 50 years old. Okay, they know that is their customer. And they live in suburban USA. And if they're one of these people, they have 1.94 children. All right. And the average BMI or body mass index for this person is 29 to 30 BMI. And this puts them in the category of overweight and probably bordering on obese. Lands' End knows this, right? Yet their catalog is filled with young, beautiful, thin, slim, fit people. They could easily hire 50-year-old overweight models and it would save them a lot of money, right? Those models are not expensive. They don't do that because it doesn't sell clothing, right? And slim, pretty young people sell clothing. And this is because in a lot of ways, clothing is aspirational. I know I don't look like the lumberjack model in the Lands' End catalog. I'm not delusional about this, but maybe I just want to look a little bit like him. And maybe that lumberjack kind of shirt is going to help a little bit. And I can dream. And look, if your job is to sell clothes, the first task is to sell the clothes, right? It does no good to give people a wonderful customer experience where they spend a lot of time on your site and they don't buy it. Make the sale, right? And Lands' End understands this. They make the sale through the catalog, and then people hate returning things. So even if it doesn't fit them and they don't look like the lumberjack, maybe they keep it and you still make money. All right. So images of yourself just may not help. You've got to test this hypothesis. And so Lands' End tested it. So maybe they did a bad job. But what about fit? Masha mentions fit, and that's a great thing. Surely this is the big problem, and it leads to a lot of cost and waste, and VTO is going to help us solve that. You know, we just don't want people buying 10 sizes and sending 9 of them back. So can people analyze fit through visual analysis. So yeah, does this sweater fit Lewis Hamilton? Well, you know, if you know Lewis Hamilton, you say, yeah, that's stylish. But most people would say that doesn't fit, right? So the fit problem through visual analysis is actually quite hard. So you have to know the preferences of people and whether or not they're Formula One drivers. But you know, surely you think showing someone an image of the clothing will help them analyze whether it fits. And I question that as to how well that works. And you know, many people have tried various things and have resorted to things like tension maps and stuff, heat maps. Your customer does not understand a heat map. They don't want to see a heat map. They don't want to learn about a heat map. They want to look at beautiful clothing and then imagine themselves in it and buy it. So I think this is a red herring. I don't think you can. There's another problem with virtual try-on and I don't care whether you're using a simple body model, this will not work on a simple body model or something else. And that is that a lot of garments are actually compression garments. And when you're buying a pair of jeans, this is the question you're asking yourself. Does it make my butt look cute? This is just the fundamental jeans question. And jeans are a form of compression garment, as are bras. And simple doesn't compress. Right, so you can virtual try on jeans on simple all day long, and your butt shape is not going to change. So you're not going to get a good answer to the question, does it make my butt look cute? And so the same goes for bras. Very hard problem, and we'd have to get really accurate physics simulation to do the deformation. So deformation garments are a limitation. The other thing is, we as humans are just total vision snobs. All right, 30% of your brain is devoted completely to vision, and probably 40 to 50% of your brain is involved in vision in some way. And only 8% of your brain is devoted to touch. So we just completely it's chauvinism. We believe the vision is the thing. But I challenge you to go into a completely dark changing room with 3 pairs of jeans. And I bet you will be able to tell me which pair fits you. You can't see them, you can touch them, you can put them on, you can squat down, you can move around. This will tell you whether the thing fits you. So in some sense, haptics is the problem, not vision, it's touch and touch perception. And we can't simulate that visually. Vision doesn't replace it. And unfortunately, there are no good haptics suits that you can wear on in your home and try on virtual garments. Nor can you have haptic touch display to feel the fabric, which is important for a lot of people. So this is a real problem. So the takeaways from this are, first of all, define your terms. Why are you doing VTO? Does that match your customer's real problem? Do you know who your customer is and what it is their goals are and why they're buying your products? Define the goal of your project. Make sure that your technology actually solves that problem and not some other problem. And then test your hypotheses the way Land's End did. Do people want to see themselves? Whatever you do, don't ask your customer if they want a virtual try-on. They will all say, yes, I want virtual try-on. They have no idea. They're not, I mean, you've got to work backwards from your customer, but your customer in this case just doesn't really understand. They want this thing because they think it's going to solve everything, but they don't really know. So test it on them and make sure that the product actually solves the problem. So that's my little speech. Hopefully that will generate some discussion at the panel later. So let's see, when is my next? Do you remember when my next talk is? It's like 2:30 or something.
Yeah, your next talk is at 2:30, so you still have like
Still have a
15.
little bit of time.
Yes.
So if I haven't dissuaded you, what if you still want to do it? And look, there are applications where there isn't, the customer is a 3D avatar and you need to clothe it because Simple looks pretty bad just as a gray mesh. I admit that as one of the creators of Simple. What we're going to do here is show you how we capture clothing. You know, obviously, well, I'll skip that. We don't want to design clothing like that. So we've been working on a series of papers. We started with something called Hood, which I'll introduce very briefly. That is a neural representation of 3D garments that lets us drape them and simulate them more flexibly, I would say, than traditional clothing packages. Contour Craft, which addresses layering of garments, and I'll talk about Gaussian garments, which appeared recently at 3DB. So Hood is the beginning of this. It's a graph neural network representation of a mesh. And this graph neural network is pretty nice in the sense that we can change the topology. So here we have zippers and buttons that we can do and undo. So it's a mesh, and everyone says meshes are no good because they don't allow you to change topology, but it's actually quite easy to change topology. The other thing is that we train this garment model in a completely unsupervised way with physical constraints. I'm not going to go into all the details of this. You can look up Artur's work on Hood, but it's a foundation for everything we do next. One of the problems with that original Hood paper is it's only a single layer garment on top of simple, and we want to have more complex multi-layer garments. And you need to resolve the interpenetration issues if you do that. You want to prevent them in the first place, and if they happen, you want to resolve them and fix them. And so we have a neural network approach for doing that called Contour Graph. And I'm not going to say these are the world's most realistic garments, but it's super easy for us now to dress people with various shapes and so on, and simulate them in things like Unreal. All right, but can we make those more realistic still? And so let's look at how we do that. This is the Gaussian garments paper, which, as I said, appeared at 3DV recently. We start with a multi-camera capture system. Okay, so this only works if you have a multi-camera capture system. So we take a bunch of images and we do standard 3D reconstruction and hole filling, and we get out a template mesh. So we start by extracting a template mesh of the garment we want, and then we initialize a Gaussian texture on top of that. So we have 3D Gaussians, which are displaced. There's a UV map, and we define these 3D Gaussians relative to the triangles on the surface. Then, given a sequence of segmented images in multi-camera capture, we track the geometry across time. We get quite accurate 3D shapes. And then we factor out lighting, and we get albedo and shading. And I'll show you that in a second. And then given all of that, we actually optimize the Hood model for the physical parameters that we've observed in the garment sequence. So given a garment sequence, we can back out or infer the physical parameters that underlie the garment. And so here are some examples of our registrations. We could deal with fluffy garments. As we see, the Gaussian representation does a pretty good job of dealing with that. We get pretty accurate tracking of the garments, I would say. Pretty nice cloth motion, really high dynamics, and looks pretty realistic. And then this is showing how we factor out the albedo and the lighting. And then you see on the right, the final rendered result. In these, the lighting shouldn't have any color in general, and should just look like smooth shading. And the albedo should look like uniform color. You know, like most separation of albedo and shading, it's not completely perfect, but it roughly captures the garment and allows us to relight it. And then using Contour Craft, so we can capture all kinds of garments in this way with this process, and then using Contour Craft, we can layer them on the body and just keep on layering them, and it resolves all the interpenetrations for us. And we can, this is all, simulation is just the Hood model on top of simple, so we can take these layered garments and apply any sequence from a mass, for example, and simulate what the motion of the garments would look like. I'm not going to go through all the comparisons with other methods, but this has more realism than the reading stuff. Okay, since I have a little bit more time, okay, we happen to have access to a multi-camera capture system. What if you don't? So what could we do? Can we do this all from an image? And can we make this really easy? And can we leverage LLMs to solve this? This will be a paper tomorrow morning called Chat Garment, and I encourage you to come talk with Si Yuan, who's here, and Yao, I don't see in the room, but I know she's around. So the Chat Garment is about estimation, generation, and editing of garments using large language models. And so here's the basic pitch for you. You've got an image and you ask your LLM, based on the image, please describe the garment. Okay, it can do that, but can it actually give you the 3D garment and the sewing pattern? I was having problems with this playing, but indeed it can. So what I'll walk you through how we do this. Show you one more example. Can you estimate the garment, the sewing pattern? And it does that. And then once it's done that, you can actually adjust with text. You could do things like adjust the length of the skirt, make it shorter, make it longer, and so on. All right, so we're going to have a text-based control, so image to 3D garment and text-based editing of the garment. Of course, there's prior work on this, Sewformer, dress code, for example, and I'll show you some comparisons with them. So what's the basic idea? The basic insight is that if you have a large vision language model and you give it an image, it's able to do things like give you text output. So what if we want something other than text? What if we want a sewing pattern? How do we get that? Well, we already know that these VLMs know enough about the garment to describe it. And they can output text. So they can have a text description of an image that's related to the garment. So how do we get text? Well, we're going to use Masha's work on garment code, which it provides a textual description of the garment, as here's a JSON file. So then all we've got to do is teach the VLM to output a JSON file with this text description. Unfortunately, my slides are automatically playing. That's the game, all right? Image in, JSON file out, which is garment code, and then we have what we want, right? So for that, we need some training data. I won't take you through the whole training pipeline, but we generate a variety of synthetic garments and then generate tons of images of them, render those images relatively realistically. We have text descriptions of them and so on. Details left to the reader. And then the way this works is given a large model, and take an image, we get some embeddings, which could be decoded into the text. And we take those embeddings and we have a projection layer that a lot of the things that you want to generate are actually numeric values, and those have to be accurate. So we take the embeddings, they go through a projection layer, we generate numeric values. We have ground truth, we put an L1 loss on those, and a cross entropy loss on the text. All right, so that gives us the training paradigm. And then this produces garments. Ours are on the right, a comparison with Sewformer and dress code to the left and middle. And it looks like ours produces slightly more realistic representations of the garments. Right? And we've quantified this as well. And then, of course, we can also do editing. Changing the sleeves, changing the collar, etc. And again, we outperform Sewformer and dress codes. Okay, so I just very quickly want to talk about hair because we've got these beautiful clothed bodies now. We still got bald simple, so that's not very much fun. So I encourage you to come to the June 14th morning poster session, where we'll talk about diff locks. This is a method that takes a single image and gives back fully 3D hair and strand-based hair very quickly. And so here's the basic model. On the left, we got a single input image in. On the right, we have 100,000 strands. Okay. Now, what people have done in the past is that they've decoded a coarse hair model in a small number of guide strands and then have an upsampling technique. We just went totally at it and decoded the full 100,000 strands. We have use a PCA representation for the strands. Not that important, it's from other work. We have a scalp model that includes the sort of the density of the hair. So it includes a scalp map for baldness. The scalp texture encodes the parameters of this strand model. So we're trying to decode that. And we have a diffusion model that uses a DynaV2 feature backend. Okay, so this whole pipeline takes an image, generates a baldness map, and a scalp texture embedding that we can decode into 100,000 strands. To train that, we needed a synthetic training data set, which Alex made in Blender with quite a lot of work. It's a Blender pipeline with 407 geometry nodes. It generates coarse strands like the ones on the left, and then samples all kinds of variations on that to create a lot of diversity. We then put this on textures, we put it in images, we light it realistically. This is very similar to what Microsoft did for their synthetic hair pipeline. But in our case, we have 40,000 hairstyles, and we make it available for research purposes. It's got the RGB images, the 3D strands, all the metadata, the materials, the textures, everything publicly released. So this is finally a hair data set that people can use for training. It's going to be a big breakthrough. So here, input image on the left, followed by our result, hair step, neural HD hair, and HAR. HAR takes text as an input. So we take the image, we generate text, and then we use that to generate the HAR result. Here's an example of the baldness map, actually producing a really nice, better fit to what is in the image. It does a pretty good job predicting things like what's going on at the back. So it's got 40,000 examples to train from. So it can make good guesses about what's going on. The front of the hair is wavy, the back of the hair is probably wavy. And so, and then of course, from a single image, we can go and generate this. And then since it's strand-based hair, we can put it immediately into Unreal Engine and do physics simulation. We can blow wind on it and so on. So that is a very quick overview of Gaussian garments, check garment, and difflocks with check garment and difflocks at the conference. So please come see us. And if we have any time, I'm happy to take questions.
Yeah. Thank you, Michael, for the excellent talk. Let's give a round of applause for Michael. We do have some time for question and Q&A session. So if you have any questions, please come to the mic at the front and ask your question. Thank you.
So since you talked about the problem in the virtual trials, there was a part missing about privacy and the overall pipeline being somewhere which is completely offline. I was just wanting your views on it.
So you're worried about privacy of customers uploading data?
Yeah. And I know it's like very different question from what you have said on so far, but I work on more stuff, edge deployment and stuff. So I was thinking about how could I make it offline with completely pipeline being like running on a local A100 server, let's say.
I see. Yeah, okay, that's a good question. Yeah, I think it depends a lot on what kind of model you're going to be using. Some of these are big at the moment, big heavy lifts in terms of compute, and it probably wouldn't work on a edge device or something.
So let's say 14 million phi model, we'll say for the website of VLM 14 million VLM model, or that's it, like
Yeah. So look, I don't have the answer to this. Obviously, if I were a business, I would want to offload compute onto my customers. That would be great. I could pitch that as privacy, but I save money, so it's a win. But I don't know. Nothing that we're doing right now would work on a customer device particularly.
But so privacy is one of the concerns too.
Yeah.
Thanks.
So, but that's also not my. That's between business and the customer as to whether they trust each other.
Yeah, that's what I started this question. Can be different. Thank you.
We have one more question. Can you please come to the mic?
Thank you for the talk. I think it's super cool that like the food model, for example, can handle the quality change and also their methods you develop for handling like intersections between the years. So I'm wondering like, what are your thoughts on potentially adapting this to, let's say, simulation of the growth of events I'm talking about a single vehicle like a cabbage or the layers. I have together.
Well, that's an amazing thing you asked me that question, because somebody came up to me yesterday saying, I've been really inspired by your simple model. And I wanted to have one for plants, and we now have one. So I haven't seen it yet. So people are thinking about this. I haven't thought about this at all. But
Keep an eye out for that.
yeah.
Thank you.
You're welcome.
We have
All
time
right.
for one last question if anybody wants. Please go ahead.
This okay.
I just wanted to ask,
I can repeat it if you like. Yeah.
just wanted to quickly ask about how you approach data collection in general. Coming from an industry standpoint, you see like 1 million images and especially hard to collect data. How do we generally approach synthetic data and real world data when especially it's hard to collect this?
Yeah, so the question is really about collecting data. I mean, when you're in industry, you obviously you can't use all these academic data sets that people are putting time into. But those academic data sets are often relatively small and not super high quality. They often are very large scale. If you're scraping the internet or something. We generate a lot of synthetic data. We're very, very big on synthetic data, both at Max Planck and at Mashup. Both places have very strong synthetic data pipelines. Our Bedlam data set is what we use for training 3D human pose and shape estimation. It's a state of the art. It produces state of the art results. You can use it without any real data at all, and it's still very competitive. So we're really big on pushing synthetic, and with Difflox, it's purely synthetic data, but it generalizes to real world. I'm not saying you need just synthetic data. You probably need some real data as well. But smaller curated real data sets together with a huge amount of high quality synthetic data feels like a good solution to your problem.
Is there any rule of thumb on?
Is there what? I'm sorry.
Rule of thumb for like
What?
this percent?
I don't know. I don't know. I would love it to be 100% synthetic because I would think make life easy, but no, I don't. Sorry. No, and all of our human data gets captured under institutional review board approvals and human subjects. They sign consent forms. It doesn't allow us to use it for commercial purposes. It depends a little bit. Sorry.
Let's thank Michael again for the very engaging talk. Next up, we have Maria Korostoleva. She's a computer graphics scientist at Meshkape, working on automated scalable apparel design. Before that, she was a postdoc researcher at the Interactive Geometry Lab in ETH Zurich, working with Olga Sorkin-Hornung. She has, like Michael has mentioned, she has authored a lot of garment-related papers in SIGGRAPH and CVPR, the most recent being AI apparel, which Gordon has also touched upon, and Rags to Riches. We look forward to Masha's talk, and let's welcome Masha with a round of applause.
This opened. Oh, should I be unmuted?
Okay, oh.
I'm gonna.
Yeah. Still problem. I am in mute. You want to?
Okay.
Sorry about that. Ethereal sounds. So this is set up?
Yeah, this is good. This is good.
Okay. Well, that's one tough act to follow. Like I'm questioning my career choices at this point. Yeah, so let's just scrap that. Let's talk about some other passion of mine, which is dancing. Jokes aside, it is it's a dance competition. And as you can see, the dance world has a lot of elaborate gowns and garments that we use for the competition setup. And these garments are super complex. They have multiple layers. They're using multiple materials, not just fabric, but also reinforcements and also decoration pieces. They have to fit very, very well to allow for the movement to be correct. And they're often captured in the wild or different lighting conditions, like on the stage or in a dance studio. And these are the types of garments that I have in mind whenever I work in my research and kind of trying to shoot for representation of a variety of garments, of complexity of the garments that we see in the real world. So when it comes to virtual try-on, obviously, what my question would be like, how we can make our system to be able to process these types of complex garments. For virtual try-on, we of course know that there are multiple different directions of how it's going. There is a bunch of work that does like image to image or video to video virtual try-on without intermediate reconstruction. I think it's better in handling, it's quite good in handling this complexity and different materials, but it cannot provide us with information of how garments actually fit a person, right? How this particular piece would fit this particular body. That's a question for virtual fitting room approaches, which I would assume often rely on a classical physics simulation, don't even use much of a learning-based systems because they would take like sewing patterns and drape it on the avatar of a customer, right? And then we can evaluate all this heat maps, which we can turn into probably some nodes that, okay, this will be tied to your waist, or this will be tools on your hips, and your jeans might fall out. That's not great. But the question is, how do we get the inputs for this type of stuff for the virtual fitting room? Not all the garments are created virtually. Not all the brands are ready to share their patterns. And what are we working with? Secondhand clothing, which is often a case in the dancing community. So there is a big question of how do we get the inputs suitable for the virtual fitting rooms from the inputs that we can easily obtain, like photos and videos. So this problem is a learning-based problem, right? This is a very difficult sort of inversion of reconstructing a garment dress shape from some inputs. And if we would think about the ideal data set we would like to have to solve this type of problem, we'd want something that have a lot of examples that can represent a lot of different modalities, right? It is labeled with images, with patterns, with 3D models, depth maps, text, and like everything that we'd like to have, right? We want it to represent large variety of designs, large variety of body sizes, and hopefully capture the different environments that we can meet in the real world. However, the problem is that, okay, maybe images and text we can obtain thanks to, the availability of this type of data on the internet. I read this directly. With generative models and LLMs can also help us with data gathering. However, when it comes to sewing patterns with 3D models, this type of data is not readily available. Sewing patterns are often behind the paywalls, or are not shared at all because they're in the private walls of the brands. It's their bread and butter. So what do we do? What we can do here is the approach that I specifically appreciate is working with synthetic data, right? We just had a nice discussion with Michael about that as well, right? So synthetic data allows us to have a very controllable data sets. It not only provides us with all kinds of labels that we embed into our generation pipelines, but also we have control over the biases that this data generates. For example, we can make sure that it actually represents the full scale of sizes and the full scale of bodies, right? In fashion, we often see that the fashion images are sort of skewed to this young, slim-fitted people, sometimes we need to be able to represent all the other body shapes as well. So how do we create synthetic data for garments? One of the options is working with garment parameterization, where we have a parametric engine that takes in irrelevant parameters like style information, length of the skirt, or body information like a waist size, and outputs a sewing pattern or a garment 3D model that corresponds to those parameters. So I've built, I worked in 2 different projects that follow this direction. I want to introduce you the later one, Garment Code, which you already heard a little bit about. So I hope I will not repeat myself too much. But yeah, by the way, I'm super excited that this amazing people talk about my work and then, yeah, sorry, fangirling moment. So Garment Code is a parametric engine that allows us to create the parametric spaces for garments. It's based on the idea that we can program a sewing pattern. So we can write a garment program that takes in those parameters and outputs a sewing pattern. It's a domain-specific language that is written as basically a Python library. It allows you to create this type of parameterization with respect to design, with respect to the body. The very important features of Garment Code is that its architecture allows to create garments as sort of a plug-and-play pieces. And it provides a bunch of different tools to help creating the geometry of panels. One reason that it works very well is because sewing pattern is a very well-structured object, right? This is a bit of a simplified definition that is used in the Garment Code just to have something to start from. It has sewing patterns represented as a set of panels, where every panel is a closed piecewise curve. Every edge of this curve is either a straight line or a smooth curve, can be an arc, can be a Bezier curve of a second or third degree. Every panel, we need to know where it's located around the body to drape it correctly. So that is described by its 6D position in the world rotation and translation. And of course, it wouldn't be a sewing pattern if we didn't have stitches. So the sewing pattern also describes the connection between the edges that represent the stitches. So this is full information about a garment from the geometric standpoint. And with this type of structure, it's fairly easy to imagine how we can program a parametric panel shape, for example, right? We can define an edge as an arc that has the length of half of the waist, right? And we can define vertical edges that have the length of the skirt that we want to have. We use these values as variables and define the edges as variables. However, imagine that we have garments that have 10, 20, 30 different panels. Defining each individual panel as a program would be quite cumbersome at this level. So the second thing the Garment Code brings apart from the programming concept is object-oriented programming concepts. So we're bringing in the concepts of abstraction and encapsulation into the garments. So let's look at the example of how this could work. Imagine we have 2 types of upper garments and 2 types of lower garments, right? If we combine them together, we can have 4 different types of full body garments, right? 2 jumpsuits, 2 dresses. But semantically, the connection between any of those upper garments and any of those lower garments have the same sort of idea behind it, right? Sort of upper to lower garment stitch. And this is how we would like to describe a complex garment. So Garment Code introduces the concept of interfaces, not for garments, where like any of the lower garment would have to implement a lower garment interface. An implementation in this case, which is the specification of which edges participate in this type of interfaces that can compose the upper to lower garment stitch, right? This allows us to encapsulate the particular implementation of lower garments behind these types of interfaces. This encapsulation allows us gives us this plug and play effect of where we can change individual elements of the garment without touching any other places. It gives us a combinatorial explosion of the designs as we add more and more elements into the parametric system. On the formal side, this concept is called a component, so it's a component class, where each component is either an individual panel, it's a leaf, right? Or it can be a stitched combination of other components. So thus building hierarchical structures, making it more and more, representing more and more complex garment elements and garments as we go up that hierarchy. The components have provide decision interfaces that describe how this component can be connected with, and may also have some optional additional information like extra geometry that it defines. Sometimes it makes sense, for example, to define the armhole together with the sleeve rather than having them in separate classes. As I mentioned, Garment Code also provides a set of construction tools, including some, just straightforward CAD tools like distributed copies, like mirroring of the geometry, but also specialized tools that work specifically for garment construction, from a super simple dart calculator, which is basically a triangle calculator, to the geometric modifications like inserting a certain shape into the edges, and for example, into the edges of the panel, and specialized tools for specifying the curves. For example, sleeve is a very particularly complex element where you need to have the curves at exactly the same length, but have different types of curvature on either side. Using the Garment Code library, we built a set of components that are parameterized with respect to style parameters and body parameters. So we have a bunch of different skirts, pants, sleeves, a ton of colors. Colors are so easy to define, so I had like 15 of them. 2 different types of tops, and it can be put all together into a uniform parametric space. This is in the form of a garment configurator. This is type of tools that can be customer facing. Of course, this is like a research prototype, so it's ugly, but overall, when you work with this configurator, all you need to do is to change semantic parameters of the design, and you can obtain sewing patterns that are fabricable without having any particular technical knowledge of pattern making here. So let's see how it finishes the transformation of a t-shirt into a jumpsuit like that. So Garment Code space has a pretty high level of variation of different designs. This is all the designs that are coming from the same parametric space. And another important feature is basically we get a design retargeting across different body shapes for free. All we need to do is to fix the parameters for the style and only change the body measurements, and we will get patterns that fit different bodies. We even made a real life experiment of that. This is dresses that were designed with Garment Code and transferred between me, Olga, and my co-author, and Yana, who was our designer, who was helping us with implementing this project. As you can see, we all 3 of us have different body proportions, but the dress fits pretty well. This is a very complicated piece for a dress because it has to follow the body curves. So now that we have a way to define parametric spaces, the next natural thing, especially today that we talk about the data sets, is that we can sample the parametric space automatically and get a bunch of sewing patterns that we can work with. Hence comes to the next project, which is Garment Code data. It's a data set with more than 100,000 different garments that are draped across 5,000 different body shapes. So it's very, very diverse. It's the largest data set that contains sewing patterns that is available publicly right now. Hopefully not for long. I'm looking forward to new advancements in this area. Going from the parametric space of sewing patterns to actually have the data set with 3D models, of course, not without its own challenges. we had quite a big team of students in ETH Zurich and our collaborators from TU Dortmund University who were working on automating, getting the body measurements of implementing additional tricks to make our simulation pipeline more robust. So that we can actually, leave it for 100,000 garments and don't have to manually check all of them. The design space is so complex that there's a lot of places where they don't actually result in sewing patterns that look like any of the garments. So we had to implement additional strategies on how to sample the design space and so on and so forth. So there was a big engineering effort that resulted in this big and valuable data set. So now that we have this data, what can we do with it? The first project in this direction that I worked with came from this phase observation, where I was trying to replicate garments, basically create a virtual double of a garment that we can reuse on a different avatars, so maybe apply different animations compared to what we captured at the beginning. And what I noticed is that sewing pattern is not only a valuable representation that fits into fashion pipelines that can be fabricated, right, that can be edited, but also it holds a lot of prior information about the garments, of how the garments are structured. And using it as part of the reconstruction process allows us to teach the network the fact that garment is actually a human-made piece made from flat pieces of fabric, and that those pieces have very particular shapes, right? So this is how, this is how Neural Tailor came about. It was the first paper I worked on that was learning-based reconstruction of sewing patterns from point clouds. Yeah, I made my life a little easier at that point to start with point clouds instead of images. Just to make sure that we actually nail the reconstruction part first and get a little bit easier inputs. However, these point clouds were very sparse. It's just 2,000 points. So we can still see how well the network can perform this type of reconstruction. Unfortunately, I don't have much time to go into the details of the network structure. Also, it's quite outdated at this point. But conceptually, yeah, we put quite a lot of effort to make sure that we reconstruct patterns as structures to have this this prior information idea put to the test as much as we can. And it was very successful. These are some examples of the reconstructions by Neural Tailor, and you can see that it can reconstruct garments that have very, very fine folds, right? Again, it's just 2,000 points. It's super sparse sampling. However, the reconstruction is, okay, first when I saw it, it was mind-blowing to me that it's working that well, you know. Another interesting feature that we found, Neural Tailor, in combination of the structural representation and attention mechanisms, it was able to generalize to a variety, to the garment types, or should I say the sewing pattern topologies that were not seen in the data during training. For example, it was able to figure out how to add sleeves to the jumpsuit, or how to remove the top from the dress and reconstruct the skirt over here. Neural Tailor received follow-up work from the community. Again, it was very, very interesting to see the results from a Sue Former, who were reconstructing patterns from images, and a dress code, who were generating garments based on text. All of these three works were trained on the first data set that I worked back in 2021. It's much smaller than the garment code data, has much simpler patterns. Once the new data set came out, the availability of complex garments increased a lot, right? I think the maximum number of panels in my first data set, which to this day I regret that I didn't put any short name to this data. Every time I have to invent something to refer to it. But anyway, like the maximum patterns were like 11 or something like 11 panels. Yeah, this one has an average of 10 panels, and the maximum I think is close to it's definitely more than 30. So, turns out that the previous approaches don't really work on garment code data, right? So as part of A4L that Gordon was introduced before, we have made some experiments of training Suformer on garment code data. When we trained it from scratch, it just didn't learn, like it just refused to train anything. So this version is fine-tuned Suformer from like that was working well in the previous data set, so we added on top garment code data, and this is the best that we could get with that architecture, right? You can sort of see the relationship of the reconstruction with the image that with the input image, but it's not a sewing pattern that is usable. And interestingly, we found that the way that the sewing patterns were represented in the prior work, when you apply that same representation to more complex garments, it contains mostly zeros. So when you train a model, your labels are 95% zero, and there's a very little bit of information there. So not surprisingly, that was not really working. So it's one of the reasons why A4L had to invest a lot of time into developing a tokenizer that actually takes care of this type of complexity and doesn't fall into a trap of like, padding everything too much into like zeroing everything out into oblivion. So I will not go into technical details. Again, there will be a poster session very soon, and Gordon have introduced the work a little bit. So this A4L has successfully solved this problem and shows that we can actually process garment code data successfully from the same inputs, reconstruct pretty convincingly, very close to the ground truth values. As Gordon mentioned, the A4L is much more than just an adaptation of the previous work to a newer data set. It has multimodal inputs. You can have text-based controls, and so on. I recommend you to check it out on the second poster session. But what I would like you to remember from my talk today, if you will take something from here, is that synthetic data seems to be a very, very powerful tool, especially in fashion tech applications, where we have a limited availability of some of the modalities that are valuable for us. And this new data can open up new applications. We could not train a learning system that recovers sewing patterns without any sewing patterns available. And another big takeaway from the line of research that I was working on is that we should not assume generalization automatically. When I was working in neural tailoring, the representation for sewing patterns seemed to be very fine to me. Like it wouldn't work. They seem to represent the definition of a sewing pattern very well. But once the more complex garments came about, turns out this does not work anymore. So we need to be vigilant and be ready that when the new, more complex data comes around, when we have layers, when we have pockets, buttons, and so on and so forth, we might need to revisit this type of questions again and develop new solutions. Thank you very much for your attention. I also thank all of my collaborators for these amazing works. I also like to mention that for both Garment Code, A4L, and my previous works, all the code is available, all the data is available, so please take good use of it. Thank you very much.
Excellent. Thank you very much, Maria. We have time for a few questions before we break for the coffee break. Any questions from the audience? Yeah, please. You can ask from there. She's going to repeat.
Like skin materials that could update except this going from how the pattern would look like. And are they consider like the material?
So the question was about consideration of materials with development of sewing patterns. Unfortunately, again, this is a very, very complex problem. So we started step by step. Currently, the patterns are not affected by the materials that we're using, so they all assume sort of that we're using one material, basically. Garment code data includes 3 different materials just to show like the main variation between very soft fabric and like very stiff fabric, which affects a lot the appearance of the garment, but unfortunately we have not yet included that into the design of the patterns. But that's a great point. It's one of the limitations of the current work, and that's something that we definitely need to consider as we iterate further on the synthetic data. Thank you.
I saw one more hand here. Yeah, please go ahead.
First of all, this was such an exciting talk. Thank you so much for sharing. I'm very right there. I wanted to ask, have you tried synthetic data on anything else other than clothing in terms of any metallic property, like accessories or anything else in fashion tech? Besides clothing, because clothing is also something that's widely discussed, but I haven't seen anything much around accessories. I wanted to hear, have you looked into synthetic data in things where it's harder to get, like, I guess like it's more harder to get that data in Melbourne.
Thank you for the compliments, and the short answer is no. Unfortunately, I have not. Yeah. So the question was if I have tried to apply the synthetic data pipelines and generation to accessories, or are they or any other parts of the human outfits, basically. Unfortunately, no, I did not. Like, my work is very much focused specifically on garments. However, I do believe that the same principles can apply to other categories of the outfits, or just other categories of objects. There's just some domain-specific parts, like, specialized tools, I don't know, for that garment code implements. It will probably not be relevant. But the concept of encapsulating different parts for them to be brought together, I'm sure that can be applied to accessories as well, especially when we have the repetitive elements like on the necklaces, right? I would love to see that happening. Like, I love this area so much, and I feel that there is not enough research that is going on into the human outfits and human appearance. And there's so many ideas, and there's just 24 hours in a day. So I would be super happy to see any of these ideas being brought to life.
Thanks, Maria. Do we have more questions from the audience? We have time for one last question. Yeah, please go ahead.
So the question is if I ever tried to collaborate with industry companies on these projects. So I assume you mean like apparel companies, because I have currently in the industry for this half a year. I work at Meshcopaint and successfully applied, this is my colleague smiling me. I am applying this work, but mainly to virtual avatars, as you can imagine. Unfortunately, I did not work with apparel companies myself. I have definitely seen the interest. I have given some talks to the companies that are either like virtual try-on companies, or they're apparel companies going into like innovation landscape. And I hope to see that. I was super happy to see that interest, but unfortunately didn't have any like common projects with them yet.
The reason I asked that is that I tried fashion tag competition 3 years ago, and then very early. And then actually my try was some parts are helpful, and then some good jury review. But in reality, what I see is that users have very difficult to use this technology and different style of fashion habits. That's very important actually. That's why they have very difficulty to adopt the way of purchase and shop. So that is the one because of this way.
Yeah, so just to repeat for the people online, there was a comment that our audience member, sorry, I don't know the name yet. That she worked with the industry before. There was an interest in that area. However, it seems that like a lot of customers don't really understand this type of technology, and they have various specific preferences. So it's important for us to collaborate with industry who have the knowledge of their customers, of what would they want to have, like how they behave, what type of choices that they do. Yeah, I completely agree with that. This, some of this research is very much like based on sometimes on our own experiences with fashion pipelines, sometimes on our imagination of how this works, right? And sometimes it's fine when we just making the first steps and trying to build a proof of concepts or even like deciding whether this type of work is worth investing more or not. But eventually, as we get closer to a representation of realistic garments and realistic body shapes, for example, we need to consider the perspective of actual end users who are there, and we might find a very interesting research problems eventually. So yeah, thank you so much for mentioning that.
Fantastic. Amazing talk, Masha. Let's thank the speaker again, and we have a very short break now, and we're going to reconvene at 3 p.m. And we will begin with the talk by Matthias and his PhD student at 3, Matthias Niesen. So you have a few minutes if you want to get some break. Thank you.
Yeah.
Surrounded. So I'm coming from the opposite side. Yes. So they're very much trying to. So I did see that in the gas station. I was like, I have been late. There was another. Or just out curious, like, some of the perspective that they kind of say was on. So they want to let them get it, I was so on. That's not very helpful. Yeah, that's what, yeah, I guess a lot of time the same. Super interesting. Thanks for the data. You just had to run this.
The next 3 days. Yeah. Okay, yeah, thank you.
Yeah, you can set it up. I'm going to send you the Zoom link so that there are also.
an email again?
Yeah, I'm doing that.
Dumb question, don't forget. For the panel stuff right there, it's a bit annoying for me, but I can still try to make it for 20 minutes, so is it okay?
You can come anytime. We will have you.
I hope that the other guys are also on time. There's like one workshop, they're like 2 talks behind right now.
Okay.
I don't mind, but another.
Okay.
Okay. But yeah, thanks for the recording.
No problem.
I know it's always a bit annoying when.
Just send you an email with the Zoom link.
One server.
Like you can imagine. Like, again, that garments there, huge section. And it's important to see them, not like human in real life, but studio writing. This is much bigger. But it doesn't understand.
Yes, yes. Do you need my audio to be on?
No,
You have a separate one, right?
I have the audio from my side.
Yeah, so I'm just gonna have the video here.
Yes.
Good audio.
Yes.
Fine. We have 30 minutes, right?
Yes. Let me know. Sure. I'll introduce you since we're at time.
Yeah, you can go ahead.
All right. Thank you, everyone. We're going to begin the second half of this workshop now. For this slot, we have Matthias Niesner, who is a professor at TU Munich, where he heads the Visual Computing Lab. Before that, he was a visiting assistant professor at Stanford University. Matthias's research lies at the intersection of computer vision, graphics, and machine learning, where he is particularly interested in cutting-edge techniques for 3D reconstruction, semantic 3D scene understanding, video editing, and AI-driven video synthesis. He has published a lot of papers in TOG, ACM-SIGGRAPH, CVPR, ECCV, ICCV, and the list goes on. But in addition to his academic impact, Matthias is a co-founder and director of Synthesia Inc., a leading startup dedicated to democratizing synthetic media generation with cutting-edge AI-driven video synthesis technology. We're excited to hear about from Matthias and his PhD student.
Well, thank you so much. Thanks for having me. I know another workshop is about virtual try-on, but in this talk I'm going to talk about how to get the avatars first. And this is not just a single effort, right? There's a bunch of people that were involved. It's still a very difficult process in order to get avatars to look like a real human. In this talk, I want to talk a little bit about the journey from reconstructing an avatar from where you have a lot of data available with multiple capture setups, and eventually trying to go to generalization where you don't have the full capture setups anymore. And I want to give you a little bit of an insight, like, you know, how the journey for us went. So we started this problem not from a machine learning standpoint, but more from a graphics perspective. So we've been working on, you know, 3D multiple models, 3D reconstruction of faces, for quite a while. And the one thing we noticed, if you want to reconstruct a pretty good avatar, you also need to capture some pretty good data first. And I think this is not a new insight. Many people have been doing this, right? Both for head avatars, for humans, and so on. And when I'm talking about avatars, I'm going to talk about our head avatars in this case, but we also have efforts where we do the whole thing on humans as well. So this is a capture setup that Tobias built. He's over there. He's going to give the second talk, part of the talk. So this is a setup where you have basically 16 high machine vision cameras, and you can capture 73 frames a second. This was pretty important to us because we wanted to have relatively high frame rates for things like blinking, fast head motion, the hair is moving around. The 7.1 megapixels, all global shutter and synchronized up to microsecond. And the lights here, they're not controllable yet. These lights are basically just blowing a lot of light in that you have, then you can deal with short exposure times. And yeah, this setup is, I don't know, probably if you putting everything together, it's maybe like costs about 100K or so, but it's not crazy expensive. It's still doable in academic research. But this is basically the multi-view captures that we wanted to get to reconstruct avatars. And again, there's no learning yet. This is only about reconstruction, having a long enough capture sequence. And from this capture sequence, we want to get an avatar that is photorealistic. In a sense, we can have another viewpoint synthesis that looks good. And we can also animate the avatar later on. And if you're talking about the data, looks something like this. So this is like 16 cameras at the same time. Yeah, this unfortunately PowerPoint structures to play the 16 videos, but they're all synchronized from the different viewpoints. And all of these ones are also pretty high resolution. So you can basically see every little hair, every beard hair. And this is not yet what the reconstruction quality is going to be, but this is basically the fidelity what we eventually want to achieve. Also, the frame rate I mentioned is pretty important to us, especially hair is still super critical, right? I mean, this is our Turing test for head reconstruction in a sense. Once you get hair at this fidelity, I think we've done a good job, but I think none of the reconstruction methods today can actually do that. And the idea of the setup was already a little bit in mind that we can capture it at scale. So we wanted to capture at least a few hundred people. In total, we took recordings that look like these. We have close to 500 now, almost 10,000 sequences, and about 15 hours total recording time. And we also try to have a reasonable diversity across gender, ethnicities, and ages. We tried the best for technical university, so I think we have about 1/3 female, not great, but we tried. And yeah, so the first task we wanted to look at is just literally getting a 3D reconstruction. No avatar yet, and you can do normal view synthesis on it. So this was 2023. This was still the time when Gaussian blending was not everywhere yet. This was kind of the NeRF time still. So we thought, okay, can we look or can we figure out the NeRF method to get a good reconstruction out of this? And yeah, we've been working on this, and it's actually surprisingly difficult. We thought, well, we have more data, and the more data you throw at it, the easier it is to reconstruct it. But it turns out with NeRFs that using MLPs in their latent scales, it turns out that the more data you throw at it eventually consumes more capacity. And you can't scale the MLPs infinitely in a sense because you eventually get vanishing gradients. So you have to find better ways how to leverage actually the additional data that you capture. And so what we did at the time is we basically built on InstantNGP. So we used a hash ensemble. So multiple hash tables, basically, InstantNGP style. And the idea was that each of these hash tables kind of, in a sense, represent different type of motion. And so the different dynamics, they get encoded in different hash tables. And hence you can then go ahead and scale the whole thing, meaning that the more data you get, the better reconstructed each hash table gets because they're kind of similar dynamics per hash table. And then at the end of the day, the whole thing learns how to blend it together. So yeah, so we have a deformation field here first. Then on my pointer, yeah, so we have here a deformation field. The deformation field is doing stuff, mapping to the canonical space. And here you basically have features like instant NGP in each of these hash tables. And then the features are being blended together, and eventually you're going to get your radiance and your density, and then you can do ray sampling like in NeRF, and you can render your images. And this takes forever to optimize. It's very slow, unfortunately. But it actually produced pretty good results. So for normal Q synthesis, yeah, these results, even up to date, I would say, are still pretty much state of the art. And yeah, you can also eventually go ahead and zoom in here, and you have pretty much all control over your reconstruction that you did. So that's the first step. First step, unfortunately, is not an avatar yet. This is just pure reconstruction of the synthesis. Now we want to go ahead and animate. So for animation, we need to find a way how to control the reconstructions. And the basic idea whenever we do this in graphics is we're going ahead and taking some underlying parametric model. There's different ones for humans. You have simple. For faces, you have flame. In this case, we're doing it for faces, which means we're using flame. And for flame, you basically get a reconstruction that looks something like this, plus a bunch of offsets. So you take this multi-view data, reconstruct or fit the flame model to it, you figure out some offsets. And the idea is then that this flame model plus offsets, the space geometry in a sense, is going to rig whatever is the quote-unquote photorealistic aspect of the appearance of top. And since this was 2024, we already realized, okay, Gaussian splatting is a big thing. So you can just go ahead and take a base mesh like this. You have a flame model, you have offsets to it. And this model essentially rigs and tells you how to animate the Gaussians that sit on top of it. And now what you have to do is you have to jointly optimize for the Gaussians, for the appearance, for the offsets of flame, for the flame parameters, and then you're getting a controllable avatar, because the idea is once you've reconstructed it, you can change the underlying geometry. And if the underlying geometry changes, then the Gaussians will move along with it. And ideally, then it still looks good if you don't deviate too much. Yeah, and this is this idea of these Gaussian avatars. You then get this in the reconstruction. And here on the bottom left, you see there's a bunch of sliders. These sliders are essentially controlling the flame parameters. It's just from the parametric model. You can go ahead and change a bunch of these ones, and now you can move the Gaussians all around with it. And as a result, you're getting a controllable avatar. So now it's not just normal field synthesis, but it is also an animatable avatar that we're getting out of it. Okay, now this is maybe interesting for design purposes, but of course the whole point of it is, oh yeah, here you see the underlying flame model, the geometry. But the whole point of this is you can also take a source actor, you track the face of a different actor, and then you could do kind of the expression transfer, take the expressions and the poses from this guy, and then use it to animate the Gaussian avatar here on the right-hand side. Here, again, left-hand side is the video, right-hand side is the avatar. Okay. So this one, in this case, looks reasonable. You see a little bit if you're looking closely, the mouth is not perfect. There's a bunch of like artifacts there. Also, if the motion becomes a little bit too massive, then it blurs out. And the reason for that is because this underlying flame model you've just seen and the geometry there doesn't quite fit the avatar. So there's a bit of a discrepancy. And so we thought, well, okay, if we can get better geometry underneath, maybe that also fixes the quality afterwards. And so in parallel, we had developed a different base model here. We call this NPHM. It's like a parametric face model based on a MLP. And that one is much higher fidelity than Flame. It's a bit more expensive to develop, but it's much more accurate. So we thought, okay, if you're using a base model that has a better, higher fidelity and better fitting reconstruction, then maybe we also get better reprojection errors, and hence the avatars that we're getting will also look, more immersive and just higher quality in general. Okay, so we just assumed, okay, can you replace Flame with NPHM? And this is basically what neural parametric Gaussian avatars are. It's the same idea. You have this underlying model and you animate the Gaussians, in this case with this NPHM. Okay, so this is an example here. So on the left-hand side, you see a driving video sequence, and on the right-hand side, you see the respective avatars. See here a few more, and you see already this one looks a lot better than before, because the geometry just matches better, you get higher fidelity, higher resolution, because you don't have this mismatch. I can very quickly go over the method. I'm not going to go into too much detail. The idea is very simple. You're running nphm, you track the geometry. There's a couple of things, how to do the tracking right, how to make sure the deformation field maps respectively from frame to frame. So there's like a cycle consistency going on to make sure the geometry and the deformation field matches. Then you have a neural parametry Gaussian field kind of on top of it. That's then anchored, and that's then driven by the respective nphm animation. And yeah, based on these dynamics, we also figure out how these Gaussians have to change. So there's kind of a small learning process involved. And then eventually you render the Gaussians, you're running the rendering process, and you get the avatar out of it. And this is pretty much the result here. Yeah, so you see again the driving video. And now you can see this is already much, much stronger because you can have way more extreme animations, and the resolutions and so on is much higher. Another cool thing is you can see here the Gaussians. So I think that's pretty cool. I don't know, it's like reconstructs basically everything. So I know I was very cool when this. Okay, all right. So this is reconstruction what we can do right now. So what's missing? This is a high-end setup. This is the downside. We don't always use a high-end setup. So can we go ahead and do the same thing what we have for these reconstruction methods? Can we do this for generalization? And yeah, Tobias is going to talk a little bit about this one.
Yes, thank you, Matthias. So we've seen now the part where using high-level studio kind of data, what you can do with it, you can get like nice novel view synthesis, you can get nice animations, but there are certain applications that you can just not do with pure optimization-based approaches. And also virtual try-on is one of those. So for more advanced applications, you basically need to learn how faces, how humans usually look like, and we want to do this in 3D. So our task for the following will be, how can we learn a prior over 3D human heads? And once we have such a prior, what you can do with it is, for example, you can sample new heads, but it's typically not the main application. You can also do like simulate image to 3D reconstruction, or which is more relevant now for a try-on, you can also edit faces. So in this example, there's a semantic segmentation input, and you can actually draw in there, and then you can sample different hypotheses, and you can already imagine, okay, you try on your own face, add glasses, or change your hairstyle. And this is enabled by having such a generative 3D prior of heads. So I want to quickly talk about how you can actually train such a prior, because this is the foundation of these applications. And the current common way, or pretty much the only way how you can really do this for 3D, is to take a large 2D image data set, like FFHQ here, and then to train a 3D generative adversarial network. And that already exists, and the most well-known variant is probably EG3D. It's like a couple of years old, and we wanted to give this thing a little update because EG3D has several downsides. It's nerve-based, it's a bit slow, and uses several tricks to make it faster after rendering. It actually renders at a small resolution and then upscales it. It's not really what you want to have really 3D 3D representation at full resolution. So we thought, okay, can we do this with 3D Gaussian splatting? And there's actually two main issues when you try to just like take EG3D and replace the 3D representation of Gaussians. And one is Gaussians are an explicit representation, so there's like a fixed number of Gaussians, but for different people, some people have hair, some people have no hair. How do you morph between hair and no hair? So that's like how do you model these topology changes across people? That's one thing. And the other thing is that these Gaussians are actually very sensitive. You can have one single Gaussian and it completely blows up during your adversarial training, and it completely destroys everything. And it's just one primitive that can basically screw up your 3D representation. For nerves, it's cannot usually happen. It's like it's a field, so like parts of the field can become empty, but it's not like there's like a huge primitive that can block everything. So we tried our best, and let's see what we came up with. And in the phase domain, you can make some assumptions. So in this case, we made the assumption that since we're modeling heads, we can actually have a template head and have the Gaussians live in the UV space of that template head. It's a quite common trick nowadays. And We then follow the classical 3D GAN approach, whereas you have a generator that takes in noise and it generates the 3D representation. In our case, the 3D representation is Gaussian attributes anchored in the UV space of this template mesh. So this is like the position, scales, color, opacity, and so on. And you then basically just collect all these Gaussians in these UV maps to get your 3D Gaussian representation. You basically just merge them all together. And to actually make this a 3D GAN, after this 3D representation is ready, you rasterize it, and your discriminator just looks at it into the comparison with the real images. Now, if you just try this, it will not work, because this whole training is very unstable, typical GAN problems. So you have to babysit the Gaussians a little bit. So we basically applied all kinds of regularizations that we could think of to make this pretty prior training really robust. And another trick that we added, or that we figured out that we have to add, is basically this, the discriminator really likes high frequency details. And one kind of failure case that emerges during training is that the Gaussians become very, very thin, because from the discriminator's perspective, it looks like high frequency detail if you have very thin Gaussians, but it also means that you have lots of holes in your 3D representation, and that's not really what you want. So what we thought of is like, we regularize the surface kind of by saying there should not be like neighboring pixels that are rendered should not come from Gaussians that are completely crazily apart. So it should be, since these Gaussians are living in the UV space, we thought neighboring rendered pixels should come from neighboring Gaussians in the UV space. And that's what this loss is enforcing. And when you train this now, which you actually can get is by sampling random latent codes, you get random 3D representations that correspond to heads. Here's an example of what this UV regularization loss looks like. If you don't train with it, you get like weird artifacts that are flying around, and you get lots of holes that you can see if you look at this UV rendering. And this additional regularization loss basically just ensures that this UV rendering is smooth. And that's a final ingredient. So now, when you walk in this latent space, this is how it looks like, and it can add glasses and change like hairstyles. It's morphing just between random identities. So that's pretty cool. And since it's a 3D Gaussian representation, it's actually super fast. So you can generate heads and render them at 1K resolution on a consumer grade GPU all in real time. So that's pretty nice if you want to have like a actual usable application in the end, where you maybe want to edit a head in 3D in real time. It's nice that you can, with 3D Gaussian, but you now have the means to do that. Just a quick comparison. So there was already 3D GANs before that, and the main advantage of this one, which we called GGHead, generalizable Gaussian heads, is that it's faster. So this is how other GANs created their heads. They also look at quite reasonable, but if you look at the actual generation times, and this is like how the time that you would have, and in real time, it takes like much longer for the other methods. And this is basically the main advantage here, is like it's this time it takes to train and render is much slower. Now going to more the virtual try-on application side. So I'm showing this cool semantic segmentation application here again because I really like it. It's from a paper called IDE 3D, and that's still built on EG3D, so it's already a couple of years old. But this application is really nice, and there's more that you can do with 3D GANs than this semantic map conditioning style. One thing that we thought of is it would be nice if you can like control the hair separately from the face, and this enables stuff like hairstyle transfer, for example, which would be a try-on application. And so we took this idea of GGHead, so it's a 3D GAN that is generating 3D Gaussian representations, and tried to create a method that has not one latent code as input, but two, one for the face and one for the hair. And they should be completely disentangled, such that you get composability. And so you basically started from just GGHead. So this upper branch here is exactly this creating Gaussians in the UV space of a template mesh, what I just explained. And now the idea is to add a second generator that now creates Gaussians that should only model the hair. And for that, there's like a separate hair template that the Gaussians live on that's also predicted. And in the end, you combine these two Gaussians. And you can see like in the rendered segmentation map that the Gaussians for the hair should be white and the Gaussians for the face are gray. Now, we noticed that to make this generation really working well, we had to add like a cross-attention information movement here, because basically the idea is the generated hair depends on the generated face, but not vice versa. And this connection here basically injects this dependency. In the end, you train this whole thing again with a discriminator. Now the disentanglement for this hair and face part comes from the fact that you can get these segmentation maps from just using an off-the-shelf segmentation network and just segmenting the whole data set. And in the end, when you want to use this, the nice thing is you now have these two inputs here that you can manipulate. So you can basically like keep face code the same and change the hair code, and then should hopefully change only the hair. So let's look at some examples. So here's, for example, one randomly sampled head on the left. Okay, I'm gonna start this slide again. Hopefully it's better. Well, okay, anyway, so you have the original 3D head here, and you have some hairstyle from some other person. So this has like more reddish kind of hair, longer hair and so on. And you only take the hair code from this person, and you take the face code from this person, and then you combine it. You see that it's like in the face, it's the same identity, but the hairstyle is different. So this is what you can do now with this 3D gun, and it's kind of, I guess, nice if you were this person, you can try different hairstyles. You can say, well, I'd like to try the hairstyle of this person, and then you can look at it in 3D even from the back. Here's another example. Basically, it's not just like reference based, and you can these latent codes are very smooth, so you can interpolate. You can say, well, I want it a little bit more like that person, and you see like there's again the reference face code and one reference hair code, and we actually go away from this reference hair code by interpolating to another hair code. Does it work? No. I would like to show this. Well, okay. Anyways, I think you got the idea. So you get editing control over your hairstyle basically in 3D. So that's pretty cool. Now before we wrap up, one last kind of application is how you actually make this usable in the end. If you have if you think of an application, you probably think of something like user takes a smartphone of themselves, takes a few pictures of themselves, and then out of this you get already a 3D avatar. And the 3D avatar then maybe with some 3D gun under hood can get some editing capabilities. We're not there yet where we can have the editing capabilities, but we are there where we can have the avatar from just like a few phone images, as you can see here. So this was an example where from just these 4 images, you actually get an animatable 3D avatar, so that's quite nice. And you can see that you can have the same expressions over different of these avatars. And you can even have some fun applications that are then again more related to try on. You can make this work even on a single image. And since we're already having pretty good image generation models, you can do your edits in 2D and then just lift it in 3D and you get a 3D avatar with the change. So here we played a bit around with how they generalize. So you see like this is a generated fairy tale woman and it does something in 3D, or it can even do the bust of Alexander or the painting of Mona Lisa. So that's, I guess, a good wrap up to see where we may be in a few years' time and playing around with these models with our own faces and see what we can do with it. Here's an overview of all the papers that we just touched upon in the talk. I'm gonna let this here for a few seconds in case someone wants to take a screenshot. And with this, we would like to thank you for your attention. This is our group at TUM Professor Matthias group of mine. And there's also open positions in our group all the time for PhDs and postdocs. So if any of these projects that we just showed resonate with you, reach out to Matthias.
Thank you, Matthias and Tobias. We have some time for like 3 or 4 questions. If anybody wants to ask, please go ahead. Any questions? Let me ask one. So Matthias, did you guys try how putting on like a clothing hat on the head and then trying to reconstruct it using Gaussian avatars?
You mean like a cover for the head?
Yeah, cover for the head, and trying to do the head movement and trying to reconstruct it, just like your Turing test for the hair.
Yeah, no, we haven't tried that yet.
Okay.
But it would be interesting.
Okay.
I think it's still tough.
Okay.
But yeah, I mean, even the reconstruction is still struggling at the moment, I think. So you can imagine, I think the Gaussians is just, for the hair, the Gaussians is just fundamentally a problematic representation because it's very inefficient, right? It's just, you need very long Gaussians in a sense. And I think it would be better if you had more like a spline-based representation or something like that. So, yeah.
The reconstruction that you showed for the hair?
I mean, it looks okay, but it's
that
not,
looks okay, yeah. That
looks
looks quite impressive, actually.
Yeah, but I think the problem is still, if you want to control it,
yeah,
right, that's still a different story. So if you're going back quickly, right, I mean, the avatars itself are good, and they also look for the real if the hair doesn't move. But as soon as you have moving hair, the whole thing becomes much more complicated,
right?
Because then you suddenly have Gaussians from different hair strands kind of intersecting with each other, and I think that's just fundamentally a problem, right? So okay, so this one looks great, right? So the hair looks amazing, but it doesn't move. It's static hair. So the thing what is still an open problem, I think, in the entire research community, if somebody moves their head around and you have very long hair, and then the hair is like intersecting with each other, and I think none of these methods can even remotely do that.
Yeah.
And I think that's just such a but it's a pretty important problem for many scenarios, right?
Right.
And so there, I think Gaussians are just not the right representation. I think there would be something better if it was spline based, so you have more compact primitives that you could do better. Like historically, we've seen like guide strands and stuff like this being used in graphics, but I think it's still challenging, and we need some. I'm not so happy with that yet.
Right. The follow-up question then would be, if we use spline, do you think that will also be able to capture the appearance and the color properly?
I guess by appearance you mean also the transparent nature
and the reflection,
yeah. I think there's 2 orthogonal parts. I think the for geometric based primitives, I think splines is a natural
That's geometric, yes.
This one I would say yes, but I think there's a separate question is like, how on earth do you store the BRDF of the hair?
Correct.
Like what is it in the BRDF of the hair? It's very complicated, right? Like how, even in classic graphics methods, what do you do? Like, okay, you need some sort of like, you need volumetric rendering probably there too, or something.
Yes.
But it's a very complicated BRDF to simulate. Like if you do this with the ray tracer, it's not so straightforward. And then the other fundamental question is basically like, okay, here everything right now is lighting is baked in. So how do we even get the BRDF reconstructed, not just for the hair, for the rest? So we built like a mini light stage right now. We just released a paper like this.
Okay.
So we can do this and it's pretty good for the face, but it's not that great for the hair yet.
Right.
Because the hair BRDF is just so complicated, and you just have interreflections and all kinds of mess. And then if you have these primitives, like if you think about it, you want to do some sort of inverse path tracing or something, like how do you even dissect this stuff? And it's just mess, right? It's very complicated.
Yes.
But it's good for us, right? That's a that means we have a few more years to do good research, so we'll see how it's going to develop, I think.
Yeah, thank you, Matthias. Do we have more questions from the audience? Last call. All right, let's thank the speakers again. Thank you very much, Matthias and Tobias. We really enjoyed your talk. Next up, we have Huamin Wang, who is a chief scientist at Style3D and leads the Style3D's global research team. His research interests include high-performance computing, high-fidelity physics-based simulations, and recently generative AI for computer graphics, vision, and machine learning. Before joining Style 3D, he was a tenured associate professor in the CSE department at the Ohio State University and a postdoc researcher at UC Berkeley. Welcome, Huami, and we look forward to your talk.
All right, thanks, Archie. Hello, everyone. It's great to be here, and it's great, especially great to see a lot of familiar faces in this room. As many of you who know me, I was in academia for many years, and then I left and I joined the industry to lead the research team in the industry. But I think that puts me in a very awkward situation today, because compared with people in this room doing research, I don't do research as much as before. And if you compare me with people in the industry, I don't know much about fashion design or pattern making or whatever. But I think I have a very, very unique strength, is that compared with research people, I know more industry. And compared with industry people, I know more research. So since I'm here today, I'm going to talk about the industry, okay? I'm going to talk about how the industry thinks about virtual trial, what are the main problems, and how we're gonna deal with those problems. So when I told to give a talk about virtual trial, the first thing came to my mind is this IEEE VR paper that we wrote 11 years ago. So the idea of virtual trial has really been hovering around for many years. And if you look at the results from today's perspective, it looks pretty bad, right? The rendering looks pretty bad, the simulation looks pretty bad, everything looks pretty bad. But I think one nice thing about this paper is that it outlines the real to sim to real framework way before the same name was used by people in embodied AI, okay? Now, what does this mean? Well, at first, we want to capture images from the real world, and we want to estimate the body, size, and the pose in the real world. And then we want to do simulation. We want to simulate the garments on the body, and we also want to do simulation of illumination so that we can render the garments realistically in 2D, on 2D images. And finally, we want to do the real composition to put photos together with rendered images to make it really nice. So that was 11 years ago. What about today, right? A lot of things get changed. And obviously, we have a much faster simulation engine. This is actually the engine we developed at Stealth 3D, and you can see that we're able to simulate digital garments on avatars realistically and also very efficiently on GPU. And together with the motion capture system, you can see that this can be a very very cool prototype for virtual trial. We can do the simulation up to 200,000 vertices, degrees of freedoms. And it can also simulate a lot of content. For example, we can simulate cloth, we can simulate soft body, soft tissue. We can also simulate rigid trims, for example, buttons, zippers on garments, and also airflow. Airflow can be very important if you do very quick movement, or maybe if you're somebody standing in a windy day, airflow can also be very important. And simulation engines today, they're also very accessible. You can find this in Unreal. You can find this in NVIDIA. We are collaborating with NVIDIA to make it available for Isaac Sim later. And we also release SDK for people to use. And here's another example. We use the simulation engine to simulate soft body tissues. You can see that you have this those garments, yoga pants, and you can see those secondary motions caused by the movement. We can simulate those secondary motions very realistically because of the motion deformation of those soft tissues. Right. So now we have better simulation engine. Does that mean we're closer to the fulfillment of virtual trial? Well, to answer this question, I think we first have to define what is virtual trial, because different people have different definitions. To me, I think virtual trial means a virtual mirror. The ultimate goal of virtual trial is to have a virtual mirror. What is the virtual mirror, right? Well, it's basically like a mirror, and you stand in front of the mirror and you can try on different garments, and you can do some performance, try different poses, and the mirror will give immediate feedback, so you can check your appearance right away. And to have this virtual mirror, there are several things we have to consider. First of all, clothing has to be super realistic. You don't want like the visual artifacts to disrupt this virtual mirror perception. And also the garments provided should be consistent with the merchandise sold by the retailer. Because if it's not consistent with the merchandise, virtual trial makes no sense for business. And the second, for the body, we have to provide proper evaluation of the pose and the shape for fitting evaluation. Now, speaking of shape fitting evaluation, this is actually a very complicated problem because fitting means comfort. But how do you evaluate the comfort? This is more like a psychological problem, right? People have different preference. And also remember that the body is soft. And it's also changing all the time. For example, if I have a very big lunch today, then my belly is definitely going to be different. So these factors, they all have to be considered to do the evaluation. And another problem is performance. If you want to provide interactive simulation, image composition, how can you do it, right? Are you going to do this on CPU? Or are you going to do this on GPU? GPU is always faster, but it's not always accessible. Another question is, are you going to use cloud computing? Cloud computing is great, but you would be relying on internet connections. So there are all kinds of issues about the developing virtual trial system. But that's just my definition, okay? Now, since everyone may have a slightly different definitions, I think it makes a little bit more sense to consider virtual trial at different levels. It's just like different levels of autonomous driving, we can have levels of different virtual trial. At the very basic level, we're just going to do virtual trial completely in 2D using images. There are lots of papers recently about this already, using generative AI to do image-based virtual trial. So this is practical. And going from L1 to L2, I think it's better to start using 3D. So at L2, we're going to use 3D garments to do virtual trial. And from L2 to L3D, the difference is that we're going to consider the body of the user rather than a virtual character. So that means we have to consider fitting at this stage. From L3 to L4, we should consider performance. We want to have interaction. And from L4 to L5, we should consider agents that can do recommendation for the user. For example, what I'm going to wear today, it will make recommendations, and it will even make some customizations if it's possible later. So depending on the different levels, we will see these being applicable to different cases. For example, at L1 and L2, I think they're mainly used for business, for internal use, primarily for virtual photo shooting. And starting from L3, since we're considering the user's body, it's mainly for consumers. So there are lots of solutions at L1, but I don't think that there are many solutions at L2. So I'm going to talk about these two options. So why 3D? Why matter? Why do we want to do 3D? Controllability is a very big reason. We want to make sure that the garments visualized is the same garment being sold by the retailer. So that's the consistency requirement. And 3D provide this control condition for AI for simulation. For body fitting, 3D is also very important. It provides the possibility for us to do the fitting evaluation.
runtime performance is also a big reason, because now 3D simulation can be done very efficiently. Rendering, ray tracing can also be done very efficiently. And also, another reason is for manufacturing. 3D is close to physical real garment, so we want to also eventually make them manufacturable. And finally, for business, we want to convince them that if you start to accumulate 3D data today, it can become reusable for business, and that can save a lot of cost for future development. And AI agent, this virtual trial agent, I think it's also important in the long-term future if we have the virtual mirror, because they will make recommendations. Suppose I'm gonna do some hiking today and it's raining, and the agent will do recommendations based on my preference and will design the garments or maybe find the proper garments for me to wear today. So that will be very helpful personal assistant in the future. So today I'm going to talk about L1 and L2 because that's the two components we're developing. Hopefully, in the future, we are going to do L3 later. So at L1, we're basically doing virtual fitting on images. So that's the typical scenario we consider. On the left side, you can see this is one photograph, and in the corner we have a bunch of garments, and we can try those garments on the body, and we can generate the result on the right side. You can see that it looks pretty realistic. It's based on some existing models. I'm gonna not say that, but basically we implement those models in our platform, and people can try use those features on our platform. But this is only just one feature we provided. We also tried try on different fabrics. For example, let's say on the left side, you have a garment, you want to try different fabric, and using AI model, we're able to generate new images with those fabrics being replaced. And we can try different poses, right? For the caricature, we can change the pose, and we can also try different backgrounds. Now, you may ask, why do we need so many different features, right? They're basically just changing those image contents in it. There are two reasons. First, if we provide these features for business, this can be very useful for virtual photo shooting. It's just like doing real photo shooting. We want to try different poses. We want to try even different facial expressions. So this is going to be controllable conditions for virtual photo shooting. The second reason of these features is going to be useful for designers to visualize their ideas in the business so they can convey their ideas with others. And this is a typical example. On the top, usually the designer have some garment image, and the designer wants to create some variations. So it will use AI to generate a bunch of style or maybe fabric variations out of it. So that's very typical when you use some existing features, like existing tools like Midjourney, you can do that, right? That's the typical scenario people are thinking about. But I would like to say that this is only one scenario designers use those features. And this typically happens to small business and online retailers. Why? Because their typical workflow involves finding best sellers. So what they do is they go to some website, find a bestseller image, and then try to generate a bunch of variations, and hopefully those variations becomes new bestsellers. And usually they do this because they don't have a very strong design team. So they want to basically try to get new bestsellers from existing ones. Now, if we're going to talk about major brands, then situations can be different. For example, let's say I have a very big brand and I have my own fabric supplier, then I can just ask my supplier to give me some fabric samples. And what I'm interested in is to see what those fabric samples looks like on some garments. And in this case, we use this fabric trial feature to try on those fabrics on different garments. So this is another scenario. And the third scenario if I'm an even bigger brand, right? I have my own fabric supplier, and I can even ask my supplier to manufacture fabrics for me. In that case, I can design graphic. And I can, for example, let's say I'm gonna design a collection of garments for the spring season. I can have some graphic design, and I can create some graphic variations, and I can create fabrics and even styles further on. So you can see that depending on the business, the design model can be very differently. So therefore, on our platform, we have a whole pipeline working flow for designers to use, going from the concept, from graphic, from garment, from fabric, all the way to images and videos. And every block is basically a generative AI feature for image trial. I'm not going to talk about those details, but you can see that you can trial different colors, different fabrics, different avatars, different backgrounds, different poses, even accessories like handbags, shoes, and headwear. So that's about L1. It's all about image-based solution. Now going from L1 to L2, we're talking about 3D solutions. And we actually experiment this 3D solution. We call it the mix match, which is basically a 3D solution we offer to business to try on different garments on the avatar to see the collection. And this is a very interesting product for business because for the business, usually they're not just designing one garment for the season. Usually they design a whole collection, right? And it's very important for them to decide the pairing of those clothing for showrooms and to convey this to the consumers. So they want this feature to basically have those combinations of different garments. And we found this to be pretty useful for brands. However, we can't call it to be a success, even though a lot of business are very interested in it. Why it's not a success? Well, because there are still a lot of challenges. One challenge is involved the use of simulation. To use the simulation, we need 3D modeling, which is obviously quite a difficult challenge. And also, how do you provide parameters for simulation? So these are the challenges at the beginning. And toward the end, we have this real to sim gap, right? Simulation and rendering can be done very efficiently, but it's still not super realistic. How do you fill this gap? So that's the third challenge we have to address. So let me first talk about how do we generate 3D content, especially sewing pattern. So what is the sewing pattern? Well, we consider sewing pattern to be composed of two components. First are those sewing panels, sewing pieces. And second, we want to also have the sewing relationships among those sewing pieces. So we know how those pieces can be stitched together, just like a fitted garment, right? And then about generating those patterns, there's a question is what type of model should we use? Should we use a generative model like a diffusion model, or should we use an agent model? And we first tried the diffusion model. There are actually a lot of work about this recently, but the difference is that we build this by considering a unified representation that combines 2D pattern with its 3D geometry. The reason we're doing this is because the modeling of 3D garments from pattern is not always straightforward. Sometimes the garments can have folds or maybe have twists. So you can't straightforwardly just create geometry from the garments, from the pattern. So we try to have this unified representation and allow us to take multimodal input, including text prompts, including image, and even from point cloud, we can actually generate patterns from point cloud. So it's a very simple model and it's very suitable for 3D modeling later on, but some limitations. For example, diffusion model always have some randomness in it, so somehow it destroyed the structure of the pattern. And another question is, how do you get high quality data, right? So these are the problems. Honestly, we don't have the answer yet. So the second option is based on an agent, the AI agent, and we get this idea from Garmin Code. So Garmin Code is actually a great paper, but it has some limitations, okay? So first, Garmin Code is not written by professionals, so those patterns are not professionally made. And second, it does not cover the full pattern space. There are some categories that are not covered. So we think about this problem. Can we use large language model to learn how to write new code similar to Garmin code by using existing Garmin code, by using instructions from professionals, and by using even textbook? And we found that actually large language model has this generalization capability to write new code, which is similar to Garmin code, but it actually expands Garmin code outside of the Garmin code domain. So it actually creates new patterns out of it. So we found that it's a very powerful way to generate new patterns. And also it's very precise, so you can actually do grading or even resizing in the future. But there also have some limitations. So I think in the future, the plan we are going to build is a foundation model that combines these two, which provides 3D geometry thanks to diffusion model, and also provides precise pattern creation thanks to large language model agent. So that's what we're working on. The next question is, suppose you already have the pattern and maybe you have some geometry, maybe you have some Sewing relationship, can you create 3D garments out of it? So we studied this problem and published last year at SIGGRAPH, is that suppose you have the geometry of some pieces, we call it seed piece, we can use the Sewing relationship to determine the rest of those pieces on the garment. So we can basically, given the pattern and given some geometry of the initial piece, we can basically reconstruct those garments. It's pretty robust, but it also has some failure cases. So these are the problems. Hopefully we can address later with the help of diffusion models that I mentioned earlier. Okay, so these are about 3D modeling part. The next question is, how do we get simulation parameters? Because simulation parameters are important to make simulation accurate. And this is actually a problem that we have been studying for many years. We actually had a very early paper back in 2011 about capturing physical material properties from the real world. And we, in the company, we actually developed such hardware, and you can see it on the right side. But the problem is about overfitting. We found that overfitting can be a very big problem. Under this context, we're talking about those parameters provided by one setting does not work in another setting. So how do we solve this problem? We collect more data and we want to obtain those parameters from those diversified settings. For example, this is a SIGGRAPH Asia paper we published a few years ago. Using a neural network, we can predict physical parameters, and we can redo the simulation, and you can see that the simulation is very consistent with the video on the left side, because of we're now using this new drip test to do the parameter estimation. And next question, the final question, is about the gap between simulation and realism, right? And we think about two ways to do this problem. One is to fill this gap in 3D, and another one is to fill this gap in 2D. So in 3D, we try to do simulation, local simulation, to make the geometry looks better. And this is a SIGGRAPH we published a few years ago. On the left side, you can see this is the original garment without details. And on the right side, we provide those details by doing local simulation.
And we started this problem even further using neural network. It was a Sigma paper last year. You can see that we can do basically the same thing, but now we're using neural networks. However, there are some limitations. For example, this model is not generalized enough. Eventually, we hope that this can be just one model that fits all. It can deal with all kinds of garments. But right now, it only handles a fixed number of garments. And also, how do we make this physically plausible when you provide new details without, for example, without self-collisions? And also, we want to make this lightweight in terms of computation power, in terms of the inferencing time. So that's about 3D, okay? And in 2D, we also want to provide the details. We want to fill the gap between simulation and realism. So here, this is a NIPS paper we published last year. On the left side, you can see this is a rendered result. You can see the 3D garments on the 3D avatar. And on the right side, you can see this is the image enhanced result. So you can see that it becomes much more realistic because of this enhancement feature. And because the input was in 3D, we can change camera view, we can change the background, we can even change facial expression quite easily. And you can see that we can also maintain consistency of those new image results.
Wait, quick time check.
Yeah.
Please. We have.
There are some failure cases though. For example, here you can see that it mixed the fold with the background. I'm gonna skip this. So I think before I end my talk, I think I want to mention a few things. So one thing is about virtual trial. A lot of people would say virtual trial is for humans, but maybe it's not true. For example, I'm not sure if you know this, but Labubu was super viral, going viral on TikTok nowadays. It's getting very popular. So maybe we could consider virtual trial for such Labubu dolls. And another thing is about Stealth 3D. So I work for Stealth 3D. Virtual trial is just one aspect we're working on. The main topic we're interested in is to consider simulation with machine learning. And we're also exploring visual effects and embodied AI and many other topics. And at the beginning of my talk, I said that this is my talk about industry for research people. So a couple of weeks later, I'm going to talk about research to industry people. So this is going to be PI Apparel in New York. This is one of the biggest fashion tech conference. So I will be there. And if you happen to be there as well, please come to my talk because I'm going to talk something else. Thank you.
Thank you, Waming, for the wonderful talk. Masha, I know you were a bit awestruck when he spoke about, so I feel your fangirl moment. Any questions from the audience before we move to the last talk of this workshop? We have time for a couple of questions. I have a question, Waming.
Yeah.
Does your VTO model also suggest deletions of cloths?
What do you mean by deletion of the clause? Like,
Does it say that the style doesn't match with something that has already been put on by your system, and the user tries to add something else, and there's incompatibility in style?
if it's in 3D, we can maintain such consistency.
Okay.
But if it's in 2D, it's not always controllable.
Okay. Yeah, please go ahead.
Of the book 10 years with L3 and L4. I was curious what your take is on for the consumer video on YouTube.
This is just an estimation. I honestly don't know. I think the fitting problem can be a huge problem. But I think there are lots of people working on human body acquisition. So maybe this can be solved, but it all depends on how it fits to the business model. Yes.
So on that line, even if you're going to fit the human body to whatever, so I'm wearing this like loose fitting clothes, how do I actually know how my body looks like underneath? Right, so that's like a huge problem when it comes to like fitting, and so many people wouldn't want to put a tight suit. There are so many things like Zozo fits and something that you put a tight fitting suit and then you go in front of the camera to get the full body distribution, but most of us won't be comfortable doing that. So
Yeah.
even in that case, estimating a human body from whatever clothes I'm wearing is a very hard problem.
Yeah, I agree. I think I'm glad that you mentioned the Zuzu suit. It's a very good practice, but I don't think it's very successful. I agree. I don't have an answer to that. I think it's a huge problem. How do we get a body measured as well?
So is there any, because I was thinking, is there any human in the loop which could make it much more easier to, this is my comfort. So will that line be not completely image-based, but like something where human can come in and then say, hey, this is my level of comfort, this is
Yeah.
the style.
Yeah, that's a good question. Actually, some business tried this before. I'm not sure if they're successful or not. So one model is based on the return. For example, you buy certain merchandise and you return, and you know, the business can assume that you return because of it doesn't fit. And that suggests something, right? Suggests that this size doesn't match your size. So then if you return many, then you can estimate your fits. But you know, it has been a while, so I guess they're not so successful. But it could be done, but it's not so easy, I guess.
One more question, but more on the pattern making, and the question also goes to Maria.
Sure.
In this case, so I was kind of anyway, so whenever we are making pattern, we estimate like something fabric is available to us. But when we can't think about sustainability industries, most of the times fabric scraps and everything is, like, I think more about sustainability, but that the limited scrap materials available when I don't have the entire fabric. What kind of, then the pattern making becomes difficult, in this case, right? I don't have the entire pattern. Is there like some line of research that goes into, hey, this is the amount of fabric that's available, how do I make a pattern out of it that could make a suit or that could make a t-shirt? Is there any research that goes along that line of research, that line of consideration?
Yeah, that's another interesting, very important question. And maybe Maria should answer it. I think she has a paper about this, like the usage of existing fabrics for sustainability. Yeah, but maybe Maria can come out.
Maybe with the, what do you think on it? Oh, yes.
Yeah, this is such a cool area, actually. Unfortunately, there's not so much research going into there, but I definitely see an interest in the research community that like acknowledges the problem, and I see students are coming and like, we want to do, you know, sustainable garments. And so there is a paper that we published together with INRIA. It's coming, this SIGGRAPH that's called Rags to Riches, which it's not exactly what you're looking for, but we were basically optimizing the patterns for reuse from existing clothing, so we can reuse some of the stitches, for example, to simplify the production, things like that. I'm recommended to check it out. And I also saw the research coming from the textile community, right? It's not so much on a technical side, but more of a design-based exploration of how this could be done. There's also a lot of interesting work that's been done by that community, so I recommended to check that out. Thank you.
All right, let's thank the speaker once again. Thank you very much, Mohammed. Next up, we have Professor Ira Kemmelmacher-Schlieserman. Ira, can I ask you to please come to the stage? Ira is a professor at UW, University of Washington in Seattle, where she leads the computer graphics, AI, and reality lab research, as well as she is a principal scientist in Google. In Google, she has invented and built the virtual try-on feature, 3D product visualization from just a few photos, and fashion generator. All of these have shipped on google.com, and I'm sure all of you have tried at least a part of it. Before that, she was in Meta, and Ira built trailers of products there, face filters, and music to hand movement generator. Ira has many accolades to her credit, but I'm not going to list all of them. Finally, I would like to conclude with some of the major awards that she has. She has been awarded the Google Faculty Award, the Madrona Prize, Key Choir Innovation of the Year Award, Best Student Paper Honorable Mention at CVPR 2021. And she has also served on AC committees and PC committees of most of the top tier conferences in both computer vision and graphics. She is a senior member of IEEE and a distinguished member of ACM. Welcome, Ira, and we look forward to your talk.
Thank you so much. That was a really long introduction. You really did your homework. How do I, can you help me?
Yeah, sure.
I only have USB-C. Work for other people?
Yeah,
Yeah.
it did.
Or maybe it does. I mean, oh no, find the mirror. It worked. Thanks, it works. Oh, brilliant. I'm going to share my,
Please share your screen and you can be on mute because I'm sharing the audio. Otherwise, it's going to echo. You can mute yourself.
and I'll just recover myself once.
Yeah, no problem.
This meeting is being recorded.
All right, hey everyone. Wait, hold on. Still-
You can share your screen.
The bottom, yeah.
But I don't know the, can you turn off your, is it happening?
Again, we tried that, but
really new ideas. All right, fixed. Sorry about that. Okay, so later on throughout the, in the last few years, we figured out how to go to more categories. We expanded to men, we expanded to bottoms, to dresses, and now we're at about 50% coverage for all of those categories. We also figured out how to do hybrid QA. In this space, we're still doing some version of manual, but there's a lot of automatic already. Cool. Let me show you some examples and like the challenges that we had. So, tops worked fine. When we moved to dresses, we thought it's going to be very trivial, but it turned out to be very, very hard actually, because first of all, dresses capture twice as much pixels. They're like just larger items. They have way more intricate details. The fabrics are more diverse. And every single like detail, it makes a big difference. And so, it took a while to figure out how to do virtual try-on for dresses specifically at scale. And just to make sure, the brand image is on the left, and then there is just 3 people here that we generated the same dress on them. And on Google, you can kind of choose your person and check out the dresses. Similarly for bottoms and suits and so on, another example, suits and bottoms wasn't as hard. There are also like very tricky cases, but it wasn't as hard as dresses. So dresses was absolutely hardest category. So the brand image on the left, and there's 4 examples here of different poses and body shapes and how we generated this suit on those people. So it works pretty well. Okay, so that was everything about models. And remember, these were just 40 people that we took their photos in a studio. But the holy grail of virtual try-on is actually to be able to run it on anyone, just like on every one of you, right? You don't want to, models are helpful, but in reality, you just want to see how it looks on you. And so I want to be able to say, like, here's an input image of Ira that my 10-year-old daughter took in my house. And it's like, I'm actually pretty good with cameras and everything, but it still has some strange lighting and it's very cropped, right? And I don't know, it's all kind of saturated. So not great, but I still want to use it because, that's what I had. And so any given garment, I would want to see how that garment looks on me. So that's very important. When we started working on it, so obviously it's something that everyone wants. When we started working on it and thinking about scale, we found quite a few challenges. And so I'll describe a few of those. And for the people that want to kind of figure out, oh, what should I work on in this space? Those challenges are absolutely unsolved by anyone. And so really cool to work on any of them. So challenge number 1 is that you allow to input millions of images of people. And apparently people are actually, not that great with taking photos of full body photos of themselves. They can have, first of all, the lighting usually is really bad. Second, all the photos are taken with the phone, and the lens of the phone is usually 25 millimeter, but all the training data and the photo shoots are usually in 50 millimeter lens. And so there is a difference there. The environment is usually pretty strange. It's like in some closets, rooms, I don't know, it's like, or sometimes you get photos on the beach, whatever people have, right? So very big variation in data. And by the way, these are generated, these are not real people. I'm just trying to show a point. The real photos are actually much worse. Especially the perspective effects in photos. So like when somebody else taking your photo, they're gonna make your head look too big, or they're gonna make you look too short. Not great for any virtual try-on experience. Or if somebody will tilt the camera like this and take your photo, you're gonna look, very, very perspective, too tall or something, too skinny. Anyway, so there's a lot of issues here, and closing this domain gap is a really interesting problem because there's again no data to connect them. Challenge number 2 is that we had to move to much faster computation than offline, and because people are not going to wait for such a long time. So that's kind of trivial. And so making all of those networks very fast is important. Challenge number 3, again, we talked about it, but basically there is it's a very big scale. So millions of people, billions of garments, you want to be able to have 100% coverage on all of those categories and more. So yeah, super excited that we were able to launch it exactly at I/O, Google I/O. It's the biggest Google's biggest conference 3 weeks ago. So you can try it yourself. If I'll have time, I can demo it. But let me show a video in a sec of Vidya, our VP of Ads and Commerce, actually doing a live demo on stage. We were one of the 2 demos on stage in this conference. It's actually very, very risky and stressful, and the team didn't sleep for like 6 months because of that, including me. But let's look at the video. She was very stressed. Cool. I think so. First of all, that was very exciting. Second, you guys should try it. Third, she did a really good job of explaining the architecture a little. So let me expand on that. So we are using a 3D model in the representation because otherwise. It's really important for us that the model will not slim, will not widen people, and so 3D was really essential there. And we are actually, I'll have a slide about it. So the 3D model was important. Okay, now people have been trying it, and I feel like they did a really good job explaining all the challenges and the kind of the good things and some of the interesting things that we're working on. So I'll play 3 videos for you guys, and then we can discuss each of them. that happened so many times when people are trying things cross-gender and trying things that they would never try in a physical store, which I found really interesting, and people are actually really excited about that. So that's one. And the second thing that he mentioned is totally true about the privacy and safety and so on. And so we're thinking a lot about on one hand, opening up to as much people as possible and like making it very open. And like I was even at some point very supportive of just even showing the errors of the model. Like, why not? People will be fine with it. But some things are too complicated. So things to work on. Okay, so the reason that's first of all really cool that it works for her so nicely. But she talks about returns. This is something that keeps coming up in virtual try-on kind of business side all the time. In fact, I feel like, I don't know, maybe like more than 10 years, maybe 20 years, people are talking about the return problem, which is a really important problem, including for climate and so on. I'm not sure. We're definitely not there yet. I don't know if it's going to affect any returns, honestly, any of our collective algorithms here. Not quite yet, but it's definitely really interesting to work towards that. And the biggest thing that we have to figure out is to understand if it actually fits the person and if it's going to look realistic. But there is also a balance here, because people sometimes don't actually want to see how it fits. They want to see some beautiful image of the of how they feel. They're gonna feel about the garment and how it's gonna make them feel and so on. So you don't always want to show ill-fitted clothing. Anyway, so it's a really interesting philosophical plus very hard technical problem. So something to. So I think he did a really good job explaining the vision of many people in this room and my own. And so it's really cool to think about in a very large scale like that. All right, a little more on the technical side. So here's the base model that we're using for Try-on-You. I'm ignoring here any SFT or fine tuning that we're doing later on, but it's pretty what you would expect. So there is person information, there is garment information, there's encoders, there's a UVIT, and there's a decoder at its basis. So one thing that is important that we did have to switch from, we used to do pixel diffusion for trial models, and it was absolutely necessary to move to latent diffusion because of speed and just compute. All right, let's talk about the more 3D things, more researchy stuff. So the two things that I really care about is to be able to get to hyper detail of garments and to be able to understand fit. So I think these are very open-ended, open problems, and it's really exciting to work on them. Now there's three basic components that we have to build before that, which are motion, basic 3D, and and zoom. In addition, as I mentioned, all the synthetic data efforts are really, really important. A quick on the video, I showed I'm not going to go into it, but here's the example I showed that if we use a video model, like a general video model, and apply it on the Tryon images, we can get pretty awesome results with some tricks and so on, but pretty awesome results. And we're kind of looking into some cool applications of that. This is the same woman in different outfits that we did Tryon. These are all Tryon results and then animated. A few other results here, where we can create different motions and so on. A lot of her. All right, a different version of motion estimation is you get an input video now of a person as opposed to an image like we defined in Tryon, and you do a full-blown video Tryon. That's a really hard problem. There are some cool results that people talked about. We have a paper, but I think there's still a way, a lot of work to be done in this space, especially in the body shape estimation side. Okay, and now we've been working recently on being able to take a video or one frame or a few frames and create a 3D version of the garment from that frame. So that seemed like to be a really interesting problem. And the way we actually started with rigid objects. So the dress that I showed here, it's non-rigid. We started with rigid products where we wanted to just take an image or two and be able to show a 3D reconstruction or a video of any product on shopping. When we started it, we said we're just going to take a few images from the catalog and we'll run NERF, right? That should work. So this is the result that we got in the beginning, the one on the left. And I thought it's really exciting, but people didn't seem to think it's looking good. So I thought it's really promising. Remember, like we don't have any, I'm talking about the catalog, right? So there is a few photos of a shoe. We don't have the cameras, we don't have the poses. We have to estimate all of that automatically. We went through many iterations, and now we're at the stage where we can generate results like the one on the right. And the way that we did it is we went from NERF to be able to estimate automatically cameras and poses, to then run NERF again. That improved the results a little bit. Then at some point, we added the whole diffusion component. In fact, we added the Tryon network inside working together with NERF. And that improved, which is kind of funny to think about it, but that worked really well. And that improved the results even more. And that worked pretty well for shoes. And so if you go now, you sometimes search, shoes on Google, you will see little spinning shoes. That's all us. I'll show it in the end if there's time. But then we decided, okay, it works so well for shoes. How about we'll do it just on any product so that people can, visualize and interact with any product out there. And it turned out to be really, all the NERF and the diffusion techniques just didn't work. It turned out to be really difficult. And a lot of it also because, general objects are hard. Shoes seem to be like actually quite easy category for techniques like that. But cameras or bags or any other category turned out to be much harder. And in fact, many of those have only one image or like two images. And that's definitely not enough for any combo of NERF and diffusion. So what we end up doing is in this space, we figured out how to use synthetic data combined with just general video model to create really nice spins. So here's an example. And the latency is much faster than the NERF plus diffusion combo. You don't need pose and so on. It does hallucinate a lot. So we're struggling with that. We're working through that. But the results are looking, the ones that work looks pretty good. For example, it could hallucinate that if there's only one, think about it, there's only one image of this camera. There's nothing that prevents the video model from hallucinating that the back of the camera has another lens, things like that. So, and when you try to use it for actual user application where it should be useful, it becomes complicated. Here's some more examples of phones and couches and bags and washing machines and stuff like that. Okay, so back to the 3D garments. So we thought, okay, let's apply the same techniques. That obviously didn't work great. None of our techniques worked, and so we just because the garment is a non-rigid item, right? So that was really hard too. So we're trying to come up with techniques that would actually create something like on the right. So here's what we came up with. If we built a video diffusion model that gets as input a single image or several images or a whole video, and it can reconstruct a garment, just the garment part. There's lots of hard problems here. So first of all, if the garment is on a person, you're going to have occlusions. By definition, the hands are going to occlude parts of the garment in different places. There's going to be quite a lot of deformations. Pose changes make it really hard. So basically, the data that you're getting looks like this after segmentation. So quite hard to work with. There is also now data. So, there's a lot of images and videos out there, but there's no corresponding assets that come with it. So you can't just say like you have pairwise and train. And the assets are not great. And the great ones, there's not a lot of them. So there's the problem of synthetic data. So here's what we came up with for now. We said, okay, there's lots of images out there. So we're going to train a model that knows how to do 2 tasks. One task, it just learns how to animate. Second task is going to learn how to take and this is only for images, real images. And then second task is going to work only with synthetic data, and it will learn how to generate 360, right? And we train it all together in a way that the garment encoder gets information for both. So the weights are optimized for both of them together. And this is how we're able to get pretty good results for taking a real image now and getting a reasonable shape, 360 shape for it. Quick architecture. So there is a video data set. There is a 3D synthetic data set, much smaller one. They all go for the usual suspects, but this garment encoder now is trained, the weights are trained together for the 2 tasks, okay? And the model knows how to output both of them. So that's the basic idea. There's a little more detail, but that's kind of the basic idea. Some examples of how it looks like on different garments. Some more examples. And then, if we have 360 novel views, we can run and reconstruct, get the normals and the depth. Obviously, there's some little like magic that need to do with input frame selection. So if you have a video and you're going to choose a single view which is facing backwards, you're not going to get good results. If you're choosing multi-view, it's going to be a little better, and so on. And we also optimize it to get as input a whole video, and then you can get a little higher quality. By the way, this example, we're showing it as a good example, but actually, if you notice, I think there is something here that is not great. So that also takes me to the limitations of this method. It is very often misrepresenting slits as pants and trying to, from some reason, the model really wants to create overalls. I have no idea. It's probably a combo of the synthetic data with the real data that makes it do that. Any unusual garment shapes will usually fail because just the way that it's a pretty basic way that we train it, and we have pretty basic synthetic data here. Very researchy project, and the resolution is pretty low. I would love it to be like way higher resolution, way higher accuracy, and so on. Here's an example of what happens with for this photo, for example, like totally an overall. All right, I'll go quickly, but so I have an obsession with getting to really high detail. And so we started this project of, it's very new, and we have some initial really cool results that I want to share. But the idea is that you get a photo of a product, and we're able to zoom in as much as possible to this product so that we'll see, I want to see like even the kind of type of fabric that it's made of. So pretty fun project. I'm just going to show some examples. I'm not going to go into details, but this one is 9x zoom in that we created. You can see all the lace and the buttons and so on. can see some of the letters on the buttons. I'll skip a few of those. I'll get to the 12x one, which is always fun to look at. Yeah, I'm done. Second. Oh, this one is my favorite one. It's 12x zoom in. Yeah, super excited about this direction. And with that, I'm going to skip some of the other examples. Thank you so much for listening. Try on you, please. Tell me your feedback. Would love to hear it. We're not going to make it right in the beginning, but it's going to get better. And I talked about those things and would love your questions. Thank you.
Amazing. Thank you very much, Ira. We enjoyed your talk. Do we have any questions from the audience before we move to the panel discussion? Yeah, we have a few show of hands. So any order. You want to go first? Please.
Wow, an impressive result on the Zoom. Any detail can you give? Like, is that an autoregressive model? Do you do it like iteratively? There's a recent work also does that autoregressively, I think, or then iteratively. And they, I think, for like, I don't know, 60x Zoom. I don't know, maybe.
Oh, cool. I haven't seen it yet. If you can
chain
send me.
of Zoom.
Chain of Zoom. Cool. Yeah,
cool.
I'll take a look.
Can
Here we're I won't get into details, but we're like basically doing a lot of diffusion, like lots of steps of diffusion to try to get to as much.
Okay, so it's a single diffusion model. Okay.
Try to multiple, yeah.
We have a question from Mike.
I've got a lot of questions, but since you're one of the few people in the world who's actually run this stuff at scale with customers, can you give us any insight into their behavior? So for example, in the thing that you had out there a year or so ago, you've got all these different models, some of them larger and so on. Do people use it? Do they use the sort of skinnier models more than the heavier models? Do they buy more clothes if they use that? Do you have any insights you can share that aren't too private, I guess?
Yeah, so are you asking about the model specifically? So I'll just talk about everything. So we have the models and then we have the on you.
I guess it's really like,
just in general.
Do people buy more clothes? Do they, do you have some insights about how this really affects consumer behavior? I guess that's what I'm asking.
So we have really, so I don't know if they buy more clothes, honestly. But we do have gazillion metrics that we are tracking and they're all positive. This is why there's a lot of investment in this area in Google. So we're very, very committed and keep pushing the on the make it better and better. And like the proof of that is that there's execs going out on stage and talking about it. Anyway, so the metrics are looking really good. People seem to we have really good feedback from people, and they especially some things that let's see, some data that might be useful. So people really like the something we don't think as much here, but people really like the be able to try different colors on their skin tone. That's a big deal, even more than the body shape, honestly. Because you can't, even if you go to a store and you try like this one thing, you're not actually going and trying like yellow and orange and purple and whatever, right? So that seems to be a big deal for people, especially, depends on like their skin tone. So they really like to choose a model based on their skin tone rather than the body shape and try all of those things. That's a thing. People appreciate people do appreciate the body shape. They also want us to be very accurate there. So that's really important. And this is why the work that you're doing and Maria's are really, really, really cool. I'm really excited about that. What else did we learn? And then they expect it to be, but probably Google, because Google, they expect it to just be everywhere. And so it takes us time to up the coverage everywhere and be able to really run it. There's honestly, a lot of the work is also the catalog is changing so frequently, like literally daily. And be able to run Gen AI stuff daily on such a huge catalog is actually, it's a really interesting engineering problem that I've learned a ton in the last few years. So there's a lot of that. Just the expectation and the bar that people have is very high. So with the models. Now with Trion and U, it's interesting. There's a little bit of a different behavior. We don't have a lot of data yet, but people are just having fun. It's all about fun for now. Literally, it just nobody cares about fit as much. Like we all care about fit in the virtual Trion space, but people see it as a like, I'm gonna try it. I'm a guy, I'm gonna try dresses. I'm gonna try some ridiculous outfit from that only like people to the Met Gala are wearing, and I'm gonna try it now because I can, and I can never do it in physical store, or it's like too expensive. I'm gonna try. People are trying like insanely expensive stuff, things like that, which is really interesting, and I really love that because it opens up kind of just, I don't know, it's like makes people happy, seems like, and so that's a cool aspect of it. But I'm sure as we grow, we'll have to make sure that it fits well, and then we have to figure out returns and all that.
Great. In the interest of time, I would request the audience to hold off to your questions during the panel discussion, because we have a few panelists who need to also run to the other workshops for their panel discussions. Let's thank the speaker again, and